Hello everyone, and I'm going to start my talk. My name is Muhammad Sharif, as you can see from the slide, and the title of my talk is Thermodynamics of a Charged Black Hole.
Excuse me, Mohammed.
Hello,
Hello, yeah. Have you been in touch with Hernando?
sorry?
Means are you means did you mail Hernando? Is he coming? Means he was your
Yes, yes,
chairperson,
yes.
right?
I have told him that there are some issues. He has also told me that there are some issues with the passcode, and I have guided him as well. And he said that you start your talk, and in case of any issues, I would uh, I'm co-chairing with him.
Okay. Okay. Thank you.
Okay, thank you. So I'm talking about thermodynamics of a charged black hole. So here is my layout of my talk. First of all, I would briefly discuss classical and black hole thermodynamics. Then I would discuss thermodynamical quantities, and then I would go to thermal fluctuation effects on these thermodynamical quantities. And finally, I would conclude the talk. So first, classical thermodynamics. Thermodynamics is one of the fundamental branches of science. It studies the interrelationship among energy, heat, and work. There are following thermodynamical properties: energy, temperature, volume, pressure, and entropy. I would first briefly discuss what are the laws of thermodynamics in classical thermodynamics. Zeroth law: if system A is brought into contact with system B and there is no change, and when system B is brought into contact with the system C, there is no change, then system A is brought in contact with the system C and there will be no change. This defines thermodynamic equilibrium and a common thermodynamic property called the temperature possessed by all the three systems. In other words, we can say that if the temperature of system A is greater than temperature of system B, and temperature of system B is greater than temperature of system C, this implies that temperature of A is greater than temperature of C, which means heat flows from the system A to B and then to C. So in other words, all the components of a system have the same temperature until the system is in equilibrium. First law: if in an isolated system heat is allowed in, there will be a rise in temperature, which is directly proportional to the heat. So if heat is pumped out, this means heat dq is less than 0, then the temperature will drop, that dt is less than 0. This gives the law of conservation of energy, that any form of energy can be converted into any other form or into heat energy, but can never be created or destroyed. In other words, we can say the total amount of energy in a physical system remains constant, but it may change from one form to another. However, this must satisfy the following mathematical relation: dE is equal to TdS plus dW. Here E is the energy, T is the temperature, S is the entropy, and W is the work done. Second law: in any process, the net change of entropy of an isolated system is always negative. That is, delta S is greater or equal to 0. So this law states that the entropy of an isolated or closed system always increases or remains constant. Third law: infinitely many steps are required to reach absolute zero of a temperature by heat pump. There are two versions of this law. First version, it is not possible for an object or a physical system to have an absolute zero temperature in a finite number of physical processes. And second version implies that if temperature approaches to absolute zero, then entropy approaches to zero. Now I would discuss these laws in black hole thermodynamics. Physically, black hole is a region with gravity so strong, not even light escapes. So black hole thermodynamics provides the interrelationship among laws of thermodynamics and black hole mechanics. So we thus have a zeroth law for black hole thermodynamics defining temperature, first law of conservation of energy, and second law defining an entropy, which is an increasing quantity. So according to the zeroth law of black hole thermodynamics, the surface gravity of a stationary black hole is constant over the event horizon. So in fact, we say that temperature is proportional to the surface gravity of a black hole. So the temperature is constant for a system in thermal equilibrium. First, it relates the energy difference of two nearby stationary black hole equilibrium states to the difference in the area of event horizon, in the angular momentum, and in the charge q. So mathematical relationship is dm is equal to kappa over 8 pi dA plus omega dj plus phi dq. This second term corresponds to the angular velocity, and here phi corresponds to the electric potential of the horizon. Obviously, this relationship holds only for rotating charged black hole. So in case of non-rotating, this term will be zero, and if it is charge is zero, then this term will also be zero. Second law, the surface area of black hole can never decrease in any process, which means dA is greater or equal to zero. We can state the analogous statement of this law: total energy of a closed system never decreases in any process. This statement is not valid once quantum mechanics comes into account, because the Hawking radiation carries off the mass and therefore reduces the surface of a black hole. Generalized second law of black hole thermodynamics is given here: the total entropy being the sum of black hole entropy and entropy of whatever may be present outside the black hole is increasing. So this is the mathematical statement of this, which is the generalization of the second law. Third law, in thermodynamics, the third law is formulated in a variety of ways. The most acceptable statement for third law in black holes is of the form: the black hole temperature cannot be reduced to zero by a finite sequence of operations. However, there was no equivalent of the third law to say that it would take an infinite number of steps to get to zero temperature. Here is the complete picture of the correspondence of these laws in classical thermodynamics and black hole mechanics. So the zeroth law, T equal to constant, in black hole, it is kappa is equal to constant. And similarly, we can see all other laws. Now I'm going to discuss thermodynamical quantity for a particular black hole, which is in fact Reisner-Armstrong black hole with nonlinear electrodynamic effects. So we define this black hole in this form. Here F is given by this quantity. Obviously, here alpha is the uh, is an important quantity uh, which in fact introduce nonlinear effects of electrodynamics. So mq alpha are the mass of black hole, charge, and coupling constant. We can recover the Rn black hole when alpha is zero but q is non-zero, Schwarzschild black hole when alpha and q both are zero, and Schwarzschild black hole with the effects of nonlinear electrodynamics when alpha is non-zero but q is zero. Now we can see from this plot that metric function provide naked singularities for both positive and negative values of alpha, which is the coupling parameter. by taking m is equal to 1 and q is equal to 1. So this is the graph of the metric function with respect to radial coordinate. Now we can obtain mass of the black hole by taking Fr is equal to 0. Here R positive is the horizon radius of black hole. We can calculate surface gravity from this F in this form, and then by using surface gravity we can calculate the temperature. Here it is. Now we see its graphical picture. We can see that Hawking temperature increases with the increasing value of the coupling parameter. As we increase alpha, it increases. Next is the entropy. We can calculate entropy through this formula. In order to analyze the thermal stability of black hole, we need to calculate heat capacity, which is given by this formula. And this is the form of the heat capacity. Now, black hole will be stable if this heat capacity is positive, and this would be unstable if this is negative. So we can see from the graph that it heat capacity diverges at this point 1.2. You can see from here, this is the graphical picture of C with respect to R positive. So this point is called devious point, where heat capacity is heat capacity diverges. So positive region before this point, I mean this region provides a stability of the black hole. So in this region we see that we have black hole with small radii. Similarly, negative region, this region is unstable. So negative region after devious point provides a black hole with large radii and which are unstable. Now we see the effects of thermal fluctuations on the thermodynamical quantities. So effects of thermal fluctuations on thermodynamical potentials of Rn black hole with nonlinear electrodynamics. So uh, we have calculated uncorrected physical quantities. Now we calculate corrected physical quantities. We can write the temperature in terms of mass. We have already calculated temperature, but now we write it in terms of black hole mass. We can calculate corrected entropy. Here S is uncorrected, S tilde is the corrected, T is the temperature, gamma and eta are parameters. We can see from here different choices of the correction parameters provide different interpretation. When eta and gamma tend to 0, we have the uncorrected entropy of black hole. When eta tends to 0 but gamma tends to 1, this provides simple logarithmic corrections. When eta tends to 1 but gamma tends to 0, we obtain second order correction terms which are inversely proportional to the uncorrected entropy of the black hole. When these both parameters tend to 1, we obtain correction terms of higher orders. However, in my study, I would discuss only the second case. So in this situation, the corrected entropy, I replace all the values in this expression, value of S, value of T, and taking gamma and eta in this way, we have the corrected entropy in this form. Now I check its behavior through graphs. Well, we have taken three graphs, or we have plotted three graphs by taking, in the first graph, we have fixed gamma. In the second graph, this is the way I'm plotting the graphs in the whole presentation. In the first graph, I'm fixing gamma and taking different values of alpha. In the second graph, I'm fixing alpha and taking different values of gamma. And in the third graph, I'm fixing alpha and gamma and taking different values of Q. And if we see from all these three graphs, we find that the entropy provides an increasing behavior. So corrected entropy remains positive for considered values of alpha, gamma, as well as Q, and hence satisfies the second law of thermodynamics under the effect of thermal fluctuation. Now we can check the modified first law of black hole thermodynamics. Modified means under the influence of thermal fluctuations. So this is the form of the modified first law. Here tau, phi are corrected Hawking temperature and electric potential. We take alpha as a new thermodynamic variable and pi is the corresponding conjugate quantity. We can define these potential functions in these forms, and when we insert the uh, values of m and other parameters, other functions, we obtain these values in this form. When we insert these values in this expression, we can see that this expression is satisfied. This means the modified first law of thermodynamics is satisfied. Now, I would like to draw the graphs of corrected temperature, and these are the plots. Again, keeping the same philosophy, keeping in the first graph gamma fixed, in the second graph, oh, sorry, in the first graph alpha fixed, second gamma fixed, and third alpha gamma fixed. And we see from the first graph that it gives a divergence point at two places, and it is negative before that and it is positive after that. But in the second and third graph, it provides in the second graph it provides increasing behavior. In the third graph it first increases and then decreases, but it also gives a divergence point. So corrected temperature of black holes with small radii are affected by thermal fluctuations, while the region after the divergence point shows that black holes of large radii are unaffected. In the second graph, corrected Hawking temperature increases monotonically with respect to the horizon radius, and with the increasing values of charge, temperature firstly increases and then shows decreasing behavior for large radii. Now we calculate Helmholtz free energy. This is the energy required to create a system at constant temperature and volume. Its mathematical form is given by, so when we replace the value of corrected entropy and after integration, we have this expression. This remains positive throughout the considered domain for increasing values of gamma and alpha. This can be seen from the first two graphs. Thermal fluctuations affect the free energy with small radii more as compared to large radii for increasing values of gamma, while for different values of alpha, it shows opposite trend. The free energy increases from negative to positive with Q. In the third graph, we see that it increases from negative to positive values. And then is the internal energy. This is the total amount of kinetic and potential energy of all the molecules in a system. Again, replacing the value of S tilde and F, we obtain this quantity. Here we see that internal energy fluctuates with the increase of correction parameter and becomes negative for large horizon radius. And this is obvious from the first graph. And in the second graph, we see that it decreases till for a certain point, then starts increasing. And the third graph, it decreases from maximum to minimum. So this decreases and remains unaffected for small values of R positive, while it shows increasing behavior for large values of alpha. In the third plot, black holes with large values of charge have less internal energy and vice versa. And next point is enthalpy. This is the total heat content of a thermodynamic system, and it is given by this expression. And we can conclude from this expression that enthalpy remains positive for different values of gamma and alpha. Without, with and without thermal fluctuations, enthalpy fluctuates. This is given in the first paragraph, first plot. It gives fluctuations. It decreases for small radii and then increases for large radii when there's no coupling parameter, but it decreases gradually and is affected only for black holes of large radii when alpha is non-zero. For increasing values of charge, enthalpy also increases and gets equilibrium position for large radii. This is given in third graph. And next is the Gibbs free energy. This is given mathematically by this expression. It shows decreasing behavior for small values of R positive, but increases for large values of R positive. Thermal fluctuations affect for both small and large radii and becomes undefined at this point. This is given in this. It is undefined at this point, 3.8. When alpha is 0, decreases and negative for small but positive for large radii. When alpha is non-zero, it affected for large radii but negligible for small radii. It increases and coincides for large radius with different charge as shown in graph 3. And finally, we discuss thermal stability. First, we show this through specific heat. And obviously, this is the corrected heat, specific heat. In the earlier, we have discussed in with uncorrected heat capacity. So here we can see we have 1.47 is the devious point from the first graph here. This is the devious point, and region before this we have stable, and region here are unstable. Similarly, we can see from here it provides stability here and instability here, and similarly here and here. We can also check stability through Hessian matrix. This is defined by this, obviously here I not equal to j, and we can define these quantities. So to determine stability, we use the trace of the Hessian matrix, which is defined by this expression, and we can calculate trace of the matrix. This is given by here, and we know that from here thermodynamic system is would be stable if this trace is positive, and we can conclude from here that black holes with small radii are unstable while large radii are stable. This is the same as we have discussed through heat capacity. These are
Mohammed, sorry, but you have only 1 minute left. Sorry.
Yes, okay. So I'm going to conclude.
Okay, thank you.
Okay, we have in fact evaluated thermodynamic potentials with logarithmic corrections through corrected entropy. Decreasing behavior of Gibbs free energy indicates spontaneous reaction inside the black hole to make it more stable. We have seen that thermal fluctuations have induced more instability in large black holes while small black holes are unaffected. We have seen through Hessian trace that Rn black hole with nonlinear electrodynamics is thermodynamically more stable than the Rn and Berdine black holes. And finally, we can conclude that all our results reduce to the Rn black hole when we make the coupling parameter 0. Thank you very much.
Okay, thank you, Mohammed. I'm sorry I was so late. We were having problems with the passcodes. Apparently, only yesterday's passcodes are working. So we have time for a very short question. Please raise your hand if you have a question. I see no hand raised. Mohammed, so thank you very much for starting the session. Let me ask you a short question. So you are using a very particular formula for the corrected for the deformed entropy. How do you get that formula?
Yes. Well, I provide the details in a very simple way.
Yeah.
There are some details that I'm going to share. Here it is the details. We need to calculate through this formula partition function, then rho. Here is the formula which provides the corrected entropy. In fact, I have skipped all these calculations and I have written down the final expression which is shown here.
Okay.
So I have yes, skipped all the correct.
Okay, I understand. Okay, thank you very much.
Thank you.
So thank you, Mohammed, for your talk. So let's continue with our second talk, which will be given by Banesh Chandran. It's about black hole thermodynamics from entanglement mechanics. So please go ahead, Banesh.
Thank you, Hernando. So I'll start sharing my screen.
Yeah.
Just a minute. Okay, I hope this is visible.
It's okay.
All right. Okay, thanks. Okay, so my name is Mahesh Chandran, and I'm a PhD student in the Department of Physics at IIT Bombay. So first of all, I'd like to thank the organizers for giving me this opportunity in this platform. And without further ado, I'll begin. So the title of my talk is basically black hole thermodynamics from entanglement mechanics. Much of this talk is based on a recent work that I published in collaboration with my supervisor, Professor S. Narayanan. And in order to give a rough idea of what this talk is about and what the paper was about, I will first give a quick motivation. I'll first describe the motivation behind our project. I'll first start off with some basics regarding entanglement so that I can bring you guys up to speed. And then afterwards, I'll talk about why entanglement is relevant in field theory, and also the context in which we decided to go ahead with entanglement as a possible route to approach black hole thermodynamics. And the second section, I will build on the formalism of entanglement mechanics, which I will use along with so here I'll also describe the model that we'll be using to simulate the physics of scalar fields propagating in an arbitrary background spacetime. And we'll finish with all the formalism involved and the quantities that we'll be introducing over here. In the next section, I'll be discussing purely the results based on these numerical simulations and how black hole thermodynamics seem to be emerging from entanglement mechanics. And finally, I'll be going through the repercussions of these results and how it can affect future lines of work. So first, I'd like to begin with some basics about entanglement, some basic introduction. So what exactly is quantum entanglement? So suppose you have a quantum state psi, which can be written as a product state. Let's assume that there is an equal sign here. Suppose you can write it as a product state of two individual subsystems. Then this state is essentially called a pure state. What this basically means is that any outcome of a measurement that is made on subsystem 1 would in no way affect an outcome of subsystem 2. But in general, in quantum mechanics, because of the fact that there are interactions with the environment and it's difficult to isolate systems in general, what you hardly get any pure state. In fact, it is more likely that you end up with a mixed state wherein you won't be able to write down this wave function as a product state. Now, there are consequences arising from this inequality. And quantum entanglement is one such consequence. And the biggest reason why this leads to some non-trivial consequence is that there will be purely quantum correlations associated with the subsystem 1 and 2, such that the outcome of one measurement will directly influence the outcome of another measurement performed on the other subsystem, and vice versa. And this is an alternate definition of entanglement that I have given here for a state psi, where observable 1 acts on subsystem 2 and observable 1 acts on subsystem 1 and observable 2 acts on subsystem 2. Now, this marks a sharp deviation from how we have come to understand classical mechanics. And so entanglement is an essential feature that is exclusive to quantum mechanics. But not just that, it is also an essential feature in quantum field theory. So in order to show that, I'll just refer to a result that Unruh and Walt showed in 2017 regarding the 2-point correlation function of a scalar field. Now, this scalar field is propagating in an arbitrary background spacetime. And Unruh and Walt show that this correlation function had a behavior that is proportional to the inverse of squared geodesic distance. Now, when we look at the limit x1 going to x2, we see that the squared geodesic distance would go to 0, and we can essentially show that this term diverges as a power law of distance between the 2 points. Now, let us circle back to the definition of entanglement that we have written here. So in the context of scalar fields, you can see that the LHS, as I mentioned earlier, would diverge as a power law. On the other hand, over here, we have a finite quantity. This is basically the square of the expectation value of the scalar field at the point x1 in the limit x1 going to x2. Now, from this, it's pretty obvious that this inequality is satisfied in the sense that the LHS is divergent and the RHS is finite quantity. So this basically tells us that not only a scalar field is entangled, it is in fact a highly entangled entity. And so entanglement plays an important part in calculations pertaining to field theory. So another important result pertaining to entanglement, pertaining to entanglement in field theory, I will be describing here, which is called the area law. So when Bombelli et al. And later on Srednicki first calculated entanglement through a measure called entanglement entropy. So about entanglement entropy, it is pretty much a standard measure that people use to calculate and quantify quantum entanglement. Even though there are several other quantities, this turns out to be the standard measure. So we'll stick to that throughout the rest of the paper, rest of the talk. So when Bombelli et al. And Srednicki later on calculated the entanglement entropy for a scalar field propagating in a flat spacetime, they were able to show that this entropy scaled linearly with respect to the area of the separating horizon. And by separating horizon, I mean the horizon that separates the subsystem 1 that we have labeled and a subsystem 2. So as soon as this was calculated, people were quick to recognize that this bore an analogy with the Bekenstein-Hawking entropy, which also seemed to follow a similar area law behavior. So this was exciting at the time because people suddenly regarded entanglement entropy as a possible explanation for why Bekenstein-Hawking entropy has an area law, and points towards the quantum origin of Bekenstein-Hawking entropy. However, as time went on, there were several other theories that came by, which could similarly and sufficiently explain the Bekenstein-Hawking entropy and the area law. So, so there seems to be a problem where Bekenstein-Hawking entropy can no longer be able to distinguish between a large number of theories that comes by. And this problem is what is known as the universality problem of black hole entropy, as Carleb would put it. So, so the motivation behind our work is basically this. We were trying to look at how, if we were trying to look at how we can give entanglement an added advantage when it comes to resolving this degeneracy. So when we thought about it, we realized that maybe we can construct other quantities arising from quantum entanglement, and which I will collectively call as entanglement mechanics, that can be calculated, and maybe, if possible, it can give rise to black hole thermodynamics. So this would not only give entanglement an added advantage, but at the same time, it will also ensure that entanglement can be shown to be a fundamental building block of space-time itself. So, okay, so I'll start off with the model that we'll be using here. This is a simplified version, just for the sake of understanding, but the calculation for black hole spacetimes is much more complicated than this. So in order to start off, I'll look at the Hamiltonian for a massless scalar field propagating in a flat spacetime in 3+1 dimensions. So if I assume spherical symmetry of the system, then I can in fact perform partial wave expansion of the scalar field and effectively reduce it to a 1+1 dimensional system. And if I go further and simplify the problem by discretizing this R, that is the radial coordinate, by writing down this equation where J is the lattice point and A is the lattice spacing, then my Hamiltonian would further simplify into this form, which is actually a recognizable form corresponding to an oscillator chain with nearest neighbor coupling. So in order to have a physical understanding of what I've done here, I have drawn a diagram over here where you can see this, where you can think of this as a two-dimensional slice of a three-dimensional region in space where the field pervades. And now you bring a separating horizon over here. The circle is the horizon that separates the in degrees of freedom and the outer degrees of freedom of the field. Now, basically what I've done here is I've replaced the field degrees of freedom everywhere with a collection of oscillators where each of the oscillators is centered at each of the grid point. And the distance between two oscillators in the grid is basically given by lattice spacing A. Now, when you take the limit A going to 0, what you get is the original system that you had, which is continuous, and field degrees of freedom are in fact infinite. And this would lead to all kinds of divergences in almost all quantities that you would calculate. So we might not be able to extract some physical information about what's going on. So it is better to keep A intact and see what happens. So once we have this Hamiltonian, it's pretty straightforward to calculate the entanglement entropy, because this Hamiltonian is in a form that is recognizable and has been worked on countlessly many times before. So the Hamiltonian over here is that of a 1D oscillator chain, which you can write like this. And the ground state would in fact take the form of a Gaussian. Now, when you perform bipartition over here, which is basically bringing a horizon that separates in degrees and outer degrees of freedom, you can write down the Hamiltonian this way. And now, in order to calculate the first quantity associated with entanglement mechanics, which is entanglement entropy, we have to first calculate something that is known as reduced density matrix, which can be obtained by tracing out the inner degrees of freedom from the total density matrix of the system. And once we have this reduced density matrix, we can go on to find the eigenvalues of the same. And the von Neumann description of entanglement is given here. Basically, it's the summation of minus P ln P, where the summation runs through all the eigenvalues of the reduced density matrix. Now, this is a standard definition, while it is not at all a unique definition of entanglement or a unique way of measuring entanglement, because there are so many other quantities such as Renyi entropy or Salis entropies, which exist, which also can be used, but then they give entanglement entropy in some limit. So you can pretty much assume that this entropy, the von Neumann entropy or entanglement entropy, is a standard definition that we can trust. Now, if we add up all the contributions from the angular modes, we can get this expression where there is a summation over 2L plus 1 times the individual entropy contributions. So now moving on to the second quantity associated with entanglement mechanics, we have taken inspiration from a definition that Mukoyama put forward in '98. So in fact, in his paper, what he did is he brought forward 4 different definitions of 4 different candidates of entanglement energy. And after finishing the calculations and obtaining the numerical simulations, what he showed was that they are in fact all proportional to each other. So what we did over here is that we introduced a pre-factor epsilon in order to account for the ambiguity or in order to account for the fact that this definition is not unique, but these definitions will be proportional to each other. And this epsilon, even though we'll fix it to be 1 for now, later on we will be able to fix it depending on some physical condition that we impose. But for now, in order to keep track of the ambiguity or in order to account for the ambiguity, we'll place this epsilon over here. Coming back to the mathematical definition of entanglement energy, what we have here is basically the normal ordered Hamiltonian corresponding to the n degrees of freedom, which is averaged over the entire density matrix. Now, to have a physical understanding of what entanglement mechanics is so I'll circle back to this diagram again and first talk about entropy. So you can think of entanglement entropy as the net change in the information content of the system upon introducing this particular separating horizon. On the other hand, entanglement energy can be thought of as a net change in the vacuum energy of the system upon introducing this horizon. And what is interesting is that both the entropy and energy associated with entanglement will only be non-zero as long as there is entanglement between these two subsystems. Now, so you can basically think of entanglement energy as some sort of disturbed vacuum energy in the presence of a horizon, or basically a measure that captures correlation energy of the system. Now, given these 2 quantities, I can in fact go ahead and define a third quantity known as entanglement temperature in analogy with the definition from StatMech. But I have not added it here because it's not really necessary to do this, as we will see at the end of this talk. In fact, all we need is just the entanglement energy and entanglement entropy. So I will not digress further into the formalism and the calculation aspects of this talk of the paper. Instead, I will jump directly to the results. So starting from the simplest case, which is that of a Schwarzschild black hole, basically you have a mass in a spherically symmetric, static, and asymptotically flat spacetime. And once we performed the numerical simulations for entanglement mechanics, what we observed was that the entropy seemed to follow an area law, and this is expected. The entanglement energy, on the other hand, varied linearly with the mass of the black hole, which is also not very surprising. And entanglement temperature derived from SND from StatMech derivations is found to vary as pi CE by CS times the Hawking temperature of the black hole horizon. Now, so these results are not very surprising in the sense that Mukoyama had already discussed it to some extent in his paper for Schwarzschild. But then, in fact, he did not notice any pattern over here that might lead to some universal results. So what we did is we went on and looked at more complicated systems, such as that of a Ricen-Nordstrom black hole. So this is basically a black hole with mass m and a charge q, and which is again in a static symmetric, spherically symmetric spacetime which is asymptotically flat. So what happened here is that in fact, there are two horizons here. In fact, we can study both these horizons, but we have only presented the results of the event horizon in this case. So when we looked at the entanglement mechanics of Rice-Nordstrom at the event horizon, what we observed is that entropy again similarly followed an area law, which is expected. Entanglement energy, on the other hand, seemed to scale linearly with respect to this quantity, which is root of m square minus q square for some reason. And entanglement temperature, on the other hand, had a proportionality with Hawking temperature of the Rice-Nordstrom event horizon. Now, one interesting thing that we noticed is that the scaling constants here, Cs and Ce, which we can fix numerically from the simulations, were found to be exactly the same as that was observed in the case of Schwarzschild. So in order to probe further, we again moved on and looked at a more complicated system now, which is a Schwarzschild black hole in a de Sitter background. So this is now asymptotically non-flat as opposed to the previous spacetimes. It's spherically symmetric, and this it's basically a charge. It's basically a mass m embedded in a region in a spacetime which is asymptotically non-flat, with basically the Hubble length is L, and the spacetime is of course static and spherically symmetric. Now, when we look at the entanglement mechanics here, what we see is that the entropy again shows an area law, unsurprisingly. Entanglement energy, on the other hand, had a behavior which went as RC minus 3m, where RC is the cosmological horizon. So I'm sorry I didn't mention this before, but Schwarzschild black hole in a de Sitter background basically has two horizons. One is the event horizon and one is the cosmological horizon, and RC is the cosmological horizon. And entanglement temperature showed a similar behavior as observed before. And again, to reinforce the result that we obtained earlier, we saw that this prefactor CS and the prefactor CE obtained from the numerical simulation seem to take the exact same values as they did in previous cases. Now, you might be wondering what this N over here is, but I won't be looking at it right now. But if you're interested in figuring out why this entropy and entanglement energy are in fact quantized, you can pose a question at the end of this talk. But I will not be discussing that here because it's not relevant to the major result that we are approaching. So, given the results that we obtained for the three cases that I've presented here, and additionally for a couple of other spacetimes that I've considered, which is there in the paper, but I have not added in the talk. Basically, this includes Schwarzschild, static de Sitter patch, Rice-Nordstrom, both the Cauchy horizon and the event horizon, a Schwarzschild black hole in an anti-de Sitter spacetime, and a Schwarzschild black hole in a de Sitter spacetime, both event and cosmological horizons. Having studied all these cases, what we were able to conclude was that there is in fact a one-to-one correspondence between the quantities that I've defined earlier pertaining to entanglement mechanics and quantities corresponding to black hole thermodynamics. Now, this particular, so of course you would know what SPH and TH is. SPH is basically the Bekenstein-Hawking entropy, and TH is the Hawking temperature. But Kumar energy is actually a classical quantity that can be thought of as a conserved charge along the time translation, conserved charge along the time-like killing vector, or basically conserved charge associated with time translational symmetry, at least for static spacetimes. And this particular energy takes into account not just the mass of the black hole, it takes into account contributions from electric field and pressure and etc. So this was surprising because what we measured here is a quantum, what we measured here is a purely quantum observable, that is an entanglement energy. And somehow this seems to be varying as a quantity that is supposed to be classically derived, which is Kumar energy. Now, I will talk more about the relevance of Kumar energy in the next slide. But for now, let us stick to the results that I'll be presenting. So another universal result that I was able to obtain was that the prefactors CE and CS are in fact exactly the same for all the spacetimes considered, and the ratio T over TH is also the same. Now, another thing you can look at here is that while entanglement energy and entropy depend on the UV cutoff A, the temperature itself is independent of the UV cutoff or the lattice spacing A. And this is quite interesting because now we have proof that as we move towards the black hole horizon, we observe some cutoff independent properties or model independent properties developing that we are able to capture in our formalism, which is a good thing. But more on that later. So for now, I'll circle back to the original definition of entanglement energy, which introduced prefactor epsilon. So here, imposing the condition that this temperature is equal to Hawking temperature, I can in fact automatically fix epsilon to be of the order of 1.26. And this basically rescales all the other constants. And finally, what we get is this result. We get a relation that connects entanglement energy and Hawking temperature and entanglement entropy. Now we can go one step further and substitute for entanglement energy and entropy over here from the expressions that we obtained in the one-to-one correspondence, and all the constants will cancel out, and in fact we get this result, which is basically the equation of state for the black hole horizon, which is Komar energy is equal to twice the Hawking temperature times the Bekenstein-Hawking entropy. Now, this is quite profound because this is a result that is obtained purely within the confines of black hole thermodynamics, and we were able to derive this without any dependence on the UV cutoff from purely quantum correlations of the matter field alone. So, in order to see how this acts as the equation of state of a black hole horizon, we can in fact substitute the expression for Komar energy and do some rearranging to obtain what is known as the SMAR formula of black hole thermodynamics. So over here, I've consolidated the results of what we have obtained. So on the first column, I have written down the entanglement structure that we obtained from entanglement mechanics. And in the second column is the thermodynamic structure that is already known. And this we are able to obtain from entanglement structure simply by appropriately defining entanglement energy, and all the constants will cancel out. The SMAR formula, as you can see here, is an equation that connects mass of the black hole, potential and pressure, and the temperature and Bekenstein-Hawking entropy of the system. So in order to conclude, I would like to say that this one-to-one correspondence that we obtained, even though it did not imply any equality of their respective counterparts, we were able to show that some fundamental results of black hole thermodynamics were exactly recovered from entanglement. So this includes the SMAR formula structure of black hole thermodynamics, as we observed over here. And in fact, you can take this equation and write down the differential form to obtain the first law of black hole thermodynamics. So having derived black hole thermodynamics from entanglement mechanics alone, this again would give entanglement added strength when it comes to resolving the universality problem that I mentioned earlier. Now, one thing that we would like to see in future is, of course, whether this new and independent derivation would take the same form for SMAR formula in higher dimensions or modified theories. And of course, another thing, or the main theme of this result is that entanglement mechanics, when we define them and when we proceeded with the calculations, we did not explicitly use Einstein's equations, but somehow, purely from the quantum correlations that are present in the matter field in the system, we were able to capture information about the dynamical properties of the background spacetime. And this is quite surprising, even though it was quite discussed before in literature here and there. For instance, Forsyth and Frollo in '98 had discussed the same thing in the context of Noether charge. So Wald had earlier shown that the Noether charge corresponding to diffeomorphism invariance of the spacetime was actually coinciding with black hole entropy. And Forsyth and Frollo, on the other hand, was able to further show that this Noether charge also happened to coincide with the Noether charge corresponding to the scalar field or the matter field in non-minimally coupled theory. So that is something that we would like to probe in order to establish this link, and in order to add another dimension to this link that we have between quantum correlations of the matter field and the dynamical properties of the background spacetime. So again, finally, I'd like to conclude saying that this not only gives entanglement an added advantage, but also at the same time sets it up as a fundamental building block of spacetime in itself. And I would like to end my talk over here. Thank you all for listening. So if you have any questions, I can take them.
Okay, thank you very much, Mahesh, for this very interesting, very detailed talk. We have a question by Charles Robson. Please go ahead, Charles.
Hi, thank you for the nice talk. I was wondering, what do you think the significance is of the fact that your entanglement energy for a charged black hole it vanishes? Seems to, if I remember your equation correctly, seems to vanish for an extremal black hole.
Correct. Yeah, in the extremal limit. So one thing is that one thing I want to point out is that in the extremal limit, the entire procedure breaks down. So in order to give some context, I'll show the procedure that I had used. So in fact, in the talk, I had mentioned that that I'll be discretizing the radial coordinate. But actually, what I'm discretizing in the case of in the course of calculations that we made is the proper length of the system, proper length of the black hole involved. So as you know, proper length is something that can only be defined in the region where FFR is positive, and it is 0 at the horizon. So what happens here is that in the extremal limit, first of all, this entire formalism breaks down because there is in fact no region where FFR is positive. And in fact, the proper length itself is 0 at the extremal limit. So you're right, this formalism breaks down in that limit. So we can approach close to the extremal limit and see what happens, in which case you can see that this entanglement energy approaches 0. But as soon as it hits the extremal limit, it either vanishes, or the right thing to say is that the formalism does not hold.
So so in the limit though, it's decreasing. So I guess even close to extremality, it's getting very small, perhaps one could say.
Yes, yeah.
Yeah.
So one consequence of using proper length is, in fact, that we will not be able to access any degrees of freedom that is within the region of FFR less than 0. So even though we might not be able to say that all contributions to energy, in fact, goes to 0 at the point, what we can say is only the correlation energy between the region FFR greater than 0 and FFR less than 0.
Okay. Okay, thank you.
Okay, thanks.
Okay, thank you, Mahesh, for this very nice talk. So we continue with our next speaker, which is Swastik Bhattacharya. And Swastik is going to talk about microscopic model building for black hole membranes from constraints of symmetry. So please, Swastik.
Thank you. I'll just share my screen.
Yeah, please. So we can see it. Very good.
Okay. You can hear me properly?
Yes, yes. Everything is fine.
Okay. Thank you. So let me start. So I will be talking about microscopic models, but let me point out at the outset that the microscopic models that I will be talking about are effective theory models. That is, they are not Planck scale models. Instead, what you can be thinking of them as, they are kind of a bridge between the Planck scale models of space-time for black holes and the classical theory of black holes. So the hope is that if this attempt is successful, it will help in bridging this distance. So why am I concentrating on the black hole membranes? So let us start from the basics, which is of course well known to everybody, at least in this session, that we all know that stationary black holes obey laws of thermodynamics. I mean, horizons of temperature, formally the laws are, the laws are exactly the same as the laws of thermodynamics. And then also the black holes radiate. The only problem is, at least one of the problem is, that the entropy scales as the area of the black hole. There are several other issues, which means that even though the laws remain the same, you can think of this as an analogy, but since Hawking radiation has been discovered, most of us would view it as something more than an analogy and a physical connection. So if you take this analogy then seriously, then you can think of the stationary black holes as thermodynamic states of equilibrium. And then, of course, it follows that the non-stationary black holes would be a state which is not in equilibrium. Now we already know from our experience in the natural world that if you have a system and you are describing the system in the low energy by a continuous medium, then this system, if it is away from equilibrium, generically behaves like a fluid, or rather a fluid description is possible for this system in the low energy limit. So based on that, we would expect that the non-stationary black hole horizon probably would behave like a fluid. And indeed, this expectation is borne out. It is seen that it behaves like a viscous fluid. This was first noticed by Damour. What he found out was when Einstein equations are projected on the black hole horizon, they give rise to Navier-Stokes equations. Well, formally, there is some slight difference, but this difference is more of a technicality, and I would not go into that. Soon, this result was generalized for other types of black holes as well. So Damour was looking at the Einstein equations on the black hole event horizon. So people looked at something called a stretched horizon, which is a time-like surface situated at a small but finite distance away from the black hole event horizon. We typically call it as denoted by membrane. So it was noted that the membrane equation is also Navier-Stokes equation. And then it was later extended to other types of horizons, and in fact generically to null surface also. Because if you think about it, any null surface you can think of as can be an horizon, act as a horizon for a particular set of observers or a class of observers. So this is the situation which we are in regarding the non-stationary black holes. And this just tells you that how this description goes. The Navier-Stokes equation for fluid is basically consists of the energy conservation equation and the momentum conservation equation. Because of viscosity, there is a dissipation term, several dissipation terms in fact. So one of them comes from the bulk viscosity term. This zeta is the bulk viscosity coefficient. The other one comes from the shear viscosity. The sigma AB is the shear, and the eta is the coefficient of shear viscosity. These terms that you see here in both these equations at the last, they are basically source terms. So the picture is as follows. There is a black hole, and some object or some matter energy is falling into it. So when it falls into it, since this is the event horizon, it acts acausally. That is, before the object falls in, the event horizon grows in size and there is a dynamics. After the object has passed through it, fallen through the horizon, everything is in equilibrium. So this is a peculiarity of the event horizon. And this might come across as surprising, but actually it is not, because the event horizon is a global concept. So you have to know the whole space-time to define the event horizon, at least in the future. So that's why this behavior arises. And this T mu nu here basically tells you the energy momentum tensor and the amount of the energy momentum which is falling through the event horizon. Also, I should note that everything here is both on the left side and the right-hand side are geometric quantities. So it is very similar to black hole thermodynamics itself, where like the surface gravity kappa, it is proportional to the black hole temperature. Similarly, you have this energy density E, and this is also a geometric quantity. It turns out that it is the expansion coefficient of the null congruence on the event horizon. It is typically denoted by theta also. And this pi a is also a geometric quantity. That T we have taken here is the killing time. So basically, then what happens is something very similar to the black hole thermodynamics. The geometric quantities again arrange themselves or organize themselves in an equation which is strikingly similar to a equation of a viscous fluid. And I should also note that the values that one gets from this zeta and eta, I mean, it just follows from the, when you project the Einstein equation on the event horizon, and Damut did it for asymptotically flat black holes. So there is a negative sign for the bulk coefficient of bulk viscosity. That is going to be of some importance later, as we will see. So now the question is, since we want to consider something beyond the fluid description, that is, maybe it is a still low energy theory, but at least it tells you about the structure of the quantum theory on the horizon. So is there an effective theory description for stationary black holes? So it turns out there is, and the reasoning goes briefly as follows, that the black hole event horizon can be thought of as a natural boundary for outside observers who never falls into the black hole. So you can set up the boundary condition, and if you do that, then it affects the diffeomorphism symmetries at the event horizon. And at the horizon, the algebra is changed. This is well known. And it is also well known that for a generic 3+1 dimensional black hole in general relativity, you will find a preferred subalgebra of diffeomorphisms, which is a diffeomorphism of a circle. That is, I will call it as S1 diffuse. So the algebra for the S1 diffuse is a one parameter algebra. And you can show that the generators of this algebra are just the Virasoro generators. So basically the algebra can be mapped to a Virasoro algebra. It's equivalent to that. So this leads to an interesting way of developing or constructing a effective theory description on for a stationary black hole. So, and Carl Lipp was the first person to do it. What he did was he postulated a 2D CFT of the black hole horizon, which has a Virasoro algebra. And from that, he derived a remarkable result that he could just calculate the entropy of this CFT using Cardy formula, because you can find out the central charge. And it turns out to be the Bekenstein-Hawking entropy. And this approach is quite generic, which Carl Lipp showed. And he also pointed out that for ADS background black holes, because in that case, you have also the ADS CFT correspondence. In that case, you can have a much more detailed understanding, and that seems to be consistent with the results of Carlip, in the sense that in the special case of ADS background black holes, everything fits in. So while we know this, now we can ask a next level question, which is that can one construct effective theories on the horizon of non-stationary black holes using symmetry? And the answer is not very clear. So what we'll do is what physicists always do when in doubt, that if you know a result and the general result is not very clear to you, you look at the neighborhood of the known result by perturbing the system a little. So we ask, what about a black hole which is perturbed from the stationary state? Can symmetry be a guide there? So from the effective theory point of view, it seems physically plausible to assume that the effective description cannot change drastically because there is nothing hinting at a discontinuity or a singularity here. So if the stationary state corresponds to a CFT, this theory, which is perturbed from it, would likely to possess also a high degree of symmetry. Now let us look at the space-time point of view, this whole situation. So we already know that for 2 plus 1 dimensional black hole space-time, there is a very large set of symmetries for the near horizon metric, and it is actually a S1 diffeomorphism symmetry. Not only that, for a 3 plus 1 dimensional black hole space-time, the situation is even better. The symmetry algebra is larger. In fact, it has been argued to be the extended BMS symmetry algebra. But there is some debate about this. But in any case, there is a consensus that you can always find an S1 diffeomorphism symmetry for the near horizon space-time. There is one other thing which I should mention. For stationary black holes, this S1 diffeomorphism symmetry, and even near stationary black holes, you can connect it to the symmetry of the azimuthal angle. So you can just think about Kerr black holes in asymptotically flat space-time. The symmetry there is the symmetry of the azimuthal angle. So this is the killing symmetry we are talking about. So if we take this as our starting point, then we can look for a theory on the perturbed horizon which also possesses S1 symmetry. But now the point is, would it be a CFT? We know that if it is perturbed, there are more interactions involved which can bring in length scale. So a priori, there is no reason for it to be a CFT. In fact, we know that a non-CFT description of a black hole horizon can also accommodate a S1 diffeosymmetry. So these types of theories, most simply, they can be found out by deforming the CFT, by perturbing with it relevant, marginal, or irrelevant terms. And such a theory also has a very high degree of symmetry. In fact, it has a Virasoro algebra. Not only that, it has a S1 diffeomorphism. You can show this for a particular momentum and infinite number of conserved charges as a result. So such theories, typically integrable theories, are well known. So this is the key guiding principle then of our work. So what we will try to do is go along this line and try to find such a theory. And then what we'll do is, this theory is already a low energy effective description. We'll go to an even lower energy limit where we'll try to catch something of the hydrodynamic properties of the black hole horizon using this theory. So what we'll do is, given the complexity of the problem, we'll settle for a toy model. So the toy model that I choose is basically like a Virasoro model. So I think what follows, at least to some extent, I would need to, it would be better if I could show the video. So just 1 second. Okay, maybe there is some problem. So let me proceed, sorry. So this model is a 2-dimensional lattice model. So you can think of it as similar to Ising model, except that there is not just one Ising model, but 2 staggered Ising lattices. By staggered, what I mean is that these 2 Ising models axes are at an angle with each other. However, there is still some similarity within that the free energy density is the same of the 2D Ising model. And it also possesses a lattice-Virasoro algebra. So the lattice-Virasoro algebra, you can take a continuum limit and it becomes a Virasoro algebra, which we know from CFT. And this corresponds to an S1 diffeomorphism symmetry. The difference with the Ising model is that the critical exponents of this Baxter model are in general different from the Ising model. However, like the Ising model itself, it also exhibits a second order phase transition, which means there are a critical point. In the continuum limit, it becomes an integrable field theory near the critical point. And it is, of course, a CFT at the critical point. So what we do then is we have to fit this to construct the model. So one can just project the two lattices. We can have these two lattices on the black hole horizon like this as shown. So you have to, of course, take care of the fact that at the equatorial boundary, the conditions are such that the spins match from both sides. Note here the azimuthal angle phi. The crucial point is that the diffeosymmetry of the Baxter model, which I have used here, has this diffeosymmetry around the same angle. What do I mean by that? What do I mean by that is there is a diffeosymmetry in this lattice around this angle phi. So if you make a rotation with phi and then you can construct a diffeosymmetry around that, the lattice model remains unchanged. It's Hamiltonian. So what is happening is something pretty interesting. This model is allowing us a geometric connection. So the geometrical symmetry of the model leads to the space-time symmetry, which is the azimuthal symmetry of the angle phi. So this is actually the reason why we chose the Baxter model. Now, why is this important? I think it would be helpful in future if we suppose want to consider some process, space-time process in the theory. So we look at some perturbations and we can, because of this direct geometric connections, we can describe the process much easily. However, even though the process can be described easily, you have to go through several dualities. So I will just very briefly mention this. So the model that I have talked about, this model is equivalent to a 1 plus 1 dimensional quantum XYZ model, which also is a spin model. And typically this model is dealt with in Euclidean spacetime. For our case, we take only a special case of this model, the XY model, which can be expressed as a theory of massive free fermions in the continuum limit. Now I want to move to the hydrodynamic limit. So what I will do is, I will just look at the mean field limit. And we already know that the Baxter model's free energy density is the same as the free energy density of the Ising model. Of course, if we make this approximation, the critical exponents and other things will get wrong. But as far as a hydrodynamic descriptions is concerned, some of the things will get right. So that's why for calculational convenience, what we'll do is we'll approximate the Hamiltonian by a scalar field phi and write it in this form. This M effective squared gives you the single length scale in the problem. Now what you can do is you can identify this with the horizon fluid. The T delta S is the delta S is the change in the energy, change in the entropy due to the infalling matter energy. And phi can be thought of as the change in the area of the horizon fluid locally. So we have got our input from black hole thermodynamics. What now one can do is, since we have a field theory, we can calculate the coefficient of bulk viscosity within linear response theory. So I should mention that this whole process works only for the homogeneous case. So this is because the model is also very crude. And the inhomogeneous case involves shear, which is too complicated to deal with at the point. So we are still looking at it. And what we can do is, there is a straightforward way to calculate this. So first, we can extend the 2D mean field theory to a 2+ one-dimensional Hamiltonian, because to do transport theory, we need to work in this Hamiltonian. The good thing about this Hamiltonian is that the thermal correlation functions remain the same, even for this 2+ one-dimensional Hamiltonian. So now what we can do is, you can just look at the stress energy tensor of the horizon fluid. There is, however, a catch. The catch is that unlike a normal fluid, the stress energy tensor of horizon fluid becomes 0 when the horizon becomes stationary, which means actually it is a delta TH mu nu. That is the deviation or the excitation of the, the energy of the horizon at its excited state away from equilibrium. So that's why I have used this formula. So then what you can do is find out the thermal equilibrium formula for this Hamiltonian and plug into this definition of zeta, which is basically taking the hydrodynamic limit for an autocorrelation function, and plug in this definition of delta T here. So you can do that. And while you do that, you have to also take into account the fact that there is a mass cap of the theory. So the pole is shifted to the mass cap actually, instead of omega going to 0, which makes the mass cap or the scale enter the expression for zeta, from which you can fix it. And you need a future boundary condition, a well-known thing for an event horizon. If you do that, then only you get the zeta to be negative. So I'm not going into the details of the calculation. I just wanted to give you an idea. An added bonus is that since the change in energy is given by T delta S, since there is a mass cap, which means that the entropy also would have a minimum quantum. So now if you look at slow changes, which corresponds to adiabatic processes, you would expect that only lowest energy excitation should be there. So there is a natural explanation for the adiabatic quantization of entropy. Also following from this, the value of the quanta is, however, not the same as what Bekenstein given, but something different. But nonetheless, the effect is qualitatively here. Okay, so now these were the main results. So one thing we should clearly recognize is its limitation. This is only a toy model for a part-out black hole, and the description I have given you works only for asymptotically flat black hole. So it can be generalized. And also the fact is that we have only calculated zeta because we have only taken into account homogeneous processes. So a very interesting problem is what happens for shear viscosity, or if you can accommodate shear. Obviously, you need an integrable theory with a much richer structure. So this would be a challenging problem, but I think a very important problem within this approach. Also, there is another point, which is that we are describing the part-out black hole as a system near the phase transition point. So it would be interesting to inquire what the order parameter physically means in this case, which is a question which as of now we do not have any clear idea of. So a better understanding of these things might even lead to physical insights. And finally, a very interesting consequence of our approach is that the Raychaudhuri equation for null congruences now can be viewed as a RG flow equation. And why is that? The reason is, recall that the stationary black hole is described by a CFT, via Carleb's approach. So if you accept that, and then if you also accept that a part-out black hole is described by a deformed CFT, then we know that a part-out black hole eventually goes over to a stationary black hole, which is cosmic censorship basically. So this process then, in the effective theory picture, this should be like a deformed CFT flowing to a CFT, that is flowing to a critical point. So that's why there should be a close connection between the Raychaudhuri equation for the null congruences on the event horizon and the RG flow equation. The physical implications of this is not clear to us. maybe the people here can also suggest something. And in ADS CFT correspondence, there are holographic RG flows where one moves from the ADS boundary, which is different, to inside. So is it possible that there is a mathematical connection to that? I don't know. So, I mean, with this query, then let me end it here. Thank you.
Thank you very much, Fastik. Very nice talk.
Thanks.
Well, we have some very short time for questions. One question only. Is there any question? I don't see any hands raised. So, Swastik, let me ask you just a very general question.
Yeah.
You started by saying that this is an effective model. This is somehow the bridge between classical and quantum model. Where exactly would you say is it is more like it is closer to the classical model than to the quantum model, or the other way around?
Well, as of now, to fix the parameters of the theory, you have to look at very closely at the classical model. But the thing is that how the whole structure can be accommodated in a quantum theory, that would become clear by this sort of model. That is the hope. And it is, of course, quite far from a theory, proper quantum gravity theory, where space-time itself can be, people look at a quantum structure of space-time and so on. But I mean, in the sense that you have to go step by step. So we would expect that there must be an energy somewhere in the middle ground, which is
okay,
like that. Yeah.
Okay, very good. Thank you very much. So we continue our session. Our next speaker is Mano Srivastava. And Mano is going to talk about back reaction of matter fluctuations in an asymptotically non-flat black hole spacetime. So Mano, welcome. Please go ahead.
Thank you. Okay.
Very good. We can see everything.
Maybe I can do this. So I'm going to talk about the work which we did last year. I did last year with Professor S. Shankar Narayan at Indian Institute of Technology, Bombay. And as you see, the title is Back Reaction of Matter Fluctuations in Asymptotically Non-Flat Black Hole Spacetime. So what the objective of the work was that if we know that if we have a quantum field in a classical black hole background, it leads to Hawking radiation. But a parallel question is that when we include a quantum field in the black hole background, what effect does it have on the background space-time itself? What is the back reaction of this quantum field on the background matrix? That question, I've put a question mark here, that although there have been a lot of interesting works in this direction, I don't think it is still very clear, or we have a very clear understanding. So in this work, what we aimed at is, even before considering the effects of these quantum fields on the background space-time, what we wanted to find out that in which region of the space-time will these quantum effects become significant. So means like yesterday there was a talk by Professor Carlo Rovelli where he had a conformal diagram where he said quantum gravity effects come into picture very close to the black hole horizon, and that the region is say it is suppressed by Planck length, the width of the region. So in this work, what we try to do is that how is that suppression directly related to the Planck length, or how is it related to the size of the black hole or some other property of the black hole? So we are trying to estimate the width of this strong interaction region. And so because the aim is that whenever a Hawking radiation calculation is done, it is assumed that there is a free field propagating on a fixed classical background. So once these quantum effects or the effects of these quantum fields start becoming significant, that assumption of a field propagating on a fixed classical background, that will have to be revisited. So the aim is to try to estimate this width somehow, and I'll describe the process. So the setup for our work is that we consider only we study only spherically symmetric metrics of the form given in equation 1, which is minus f of r dt square plus dr square by f of r plus r square d omega square, where d omega square is just the two sphere, and it can be written in terms of the tortoise coordinates as in the second part of equation 1. And we know that means the title of the talk was for asymptotically non-flat black hole spacetime. So what we do is that for a usual short-side black hole, f of r in units, geometrized units, where we set the Newton's constant and the speed of light to 1, we know that f of r is 1 minus 2m by r, only the first two terms. But if we have what I call the SADS case, SADS stands for short-side anti-de Sitter black hole. So for the SADS case, the f of r is given by 1 minus 2m by r plus r square by L square, where L is related to the background curvature of the ADS space. And for the SDS case, that is short-side de Sitter black holes, the f of r is given by 1 minus 2m by r minus r square by L square. So for metrics of the form 1, we know that the position of the event horizon is determined by setting f of r equal to 0. For the usual short-side black hole, we set 1 minus 2m by r equal to 0, which gives us r is equal to 2m as the location of the horizon. For the SADS case, what we get is actually a cubic equation, but it turns out that there is only one real positive root of this cubic equation, and therefore we have only one horizon for the SADS case. Whereas for the SDS case, that is short-side de Sitter case, there again it is a cubic equation, and it turns out there are two real positive roots. And therefore, for the short-side de Sitter case, there are two horizons. One is the usual black hole horizon, and one is the usual de Sitter cosmological horizon. So now this slide was to describe what our background space-time is, or background black hole space-time is. Now the next step is to introduce a quantum field, quantum scalar field in the picture. And we assume a massless quantum field, and the dynamical equation governing the field is just the wave equation given in equation 5. And equation 5 we can decompose in terms of, if we decompose the field in terms of spherical harmonics YLM, it is well known that we can get Schrodinger-like equation in the radial coordinate, which is given by equation 6. Now equation 6 has a potential where the potential form is given in equation 7, which is f of r 1 by r df by dr plus ll plus 1 by r square. So what I want to highlight here is that this potential is L dependent. So here what I've done is I've plotted this potential for our usual short-side black hole. And there are two things which I want to point out. One, the first thing is to note is that we have a potential barrier-like situation in our system. And there is a barrier, and the potential after that goes down. And the second important thing what I want to highlight is that again the potential is L dependent. The more the value of L, the higher is the barrier height. So if given say a fixed energy E, the higher L modes, the high L modes will face a higher potential barrier and therefore will be exponentially suppressed in most cases. And therefore for our analysis, as it will turn out later, that the relevant modes for us which will not be exponentially suppressed will be only till a particular L, say from L is equal to 1, 2, 3, 4 to L max. And anything above that, the modes will be exponentially suppressed. So we have the background space-time now. We have introduced a scalar field. Now I said the aim of the work was to find the width around the region where the back reaction of the quantum field will become significant. And we want this length scale or this width to be coordinate independent. So we express it in terms of the invariant distance, which is given by equation 8. And this invariant distance is from the location of the horizon to a particular R. And we will describe, or we will study this width in terms of this gamma, which is the invariant distance. So to compute this length scale or compute this width, in our work, we did it using two approaches. One of them is a statistical mechanics analysis, and the other is a quantum field theoretic approach. So what I'll do is the statistical mechanical approach is fairly straightforward. And I'll just briefly discuss this approach and try to give key steps. But the quantum field theoretic approach, I'll go a little more in detail. So in the SM approach, that is the statistical mechanics approach, what the key steps are the following. First of all, the first step is to estimate the number of relevant modes. I said when I showed the picture of the potential that there will be some modes that will be relevant, some modes will be exponentially suppressed. So first of all, what we do is we estimate this number of relevant modes and we compute the corresponding total energy or the total ensemble average of these relevant modes, total ensemble average energy of these relevant modes. And why we call this the statistical mechanics approach is mainly because in statistical mechanics, we know that once there is an ensemble average, there will be statistical fluctuations over that average. So therefore, once we have an average ensemble energy, we have statistical fluctuations over that ensemble average. And these statistical fluctuations in energy will indirectly lead to statistical fluctuation in the mass of the black hole. And so what we show, step 3 is slightly of a detour, but in step 3, what I want to highlight is that these fluctuations indirectly lead to a smearing of the horizon. What I mean by smearing of the horizon is if you consider a very basic case of the usual Schwarzschild black hole, the horizon is at r is equal to 2m. So if there are some statistical fluctuation in the mass, say m goes to m plus delta m, then your horizon radius will also change from say r is equal to 2m to r is equal to 2m plus 2 delta m. And that delta m is a statistical fluctuation. It can increase, decrease, and things like that. So what this statistical fluctuation is doing is it is also creating a somewhat uncertainty in the horizon radius. And that is what I'm calling as the smearing of the horizon. Now, coming back to the calculation of the width, what we do is once we have these statistical fluctuations, we analyze two wave equations. So as I showed, one of the wave equation is equation 6. What we have done in the wave equation, we have considered a metric which is given by this equation 1, and f of r is just 1 minus 2m by r plus r square by l square, or means here what we have done in this f of r, we have not included any fluctuation effects, which leads to equation 6. Now, another wave equation we construct in which what we do is this f of r, we include the plus delta m effects, that is the fluctuation effects, and then we substitute it back in equation 5, and corresponding to equation 6, we will get a perturbed or a fluctuated wave equation. So in step 4, what we do here is that we compare these two wave equations. We compare the corresponding coefficients, and the region where the coefficients are very similar of the two wave equations, we conclude that there are no significant effects of the quantum fields, and therefore in that region the effects are negligible. But we do find some region very close to the black hole where the coefficients differ significantly, and that region helps us to fix that width of the strong interaction region, or the region at which the back reaction of the quantum fields becomes significant. So this is the flow of the statistical mechanics approach, and I'll display the result towards the end after I discuss the QFT approach. Now in the QFT approach, means it is a totally independent approach, and what we do is that we know that there is a black hole, we introduce a quantum scalar field, so there will be these Hawking atmosphere, Hawking particles around the black hole horizon. And what we do is we consider an external massless particle falling in towards the black hole. This is an external particle which is introduced just for the purpose of our calculation. So the motivation behind introducing this massless particle is that when this massless particle is, say, going towards the horizon, at some point close to the black hole, it will start interacting with these Hawking particles. So the region where the interaction between the Hawking particles and this massless particle, where these interactions are strong, in that region, we can say that this massless particle is seeing something more than the black hole. So therefore, in that region, we can say that the effects of this quantum scalar field is becoming significant. Whereas the region where the interaction is weak, we can conclude trivially that the effect of the quantum fields are negligible. So using this motivation, I'll just describe the key steps. So the key steps in this is, first of all, instead of dealing with, we assume that everything of this massless particle coming in, interacting with this Hawking particle, everything is happening very close to the horizon. So first thing we do is instead of dealing with the complete metric, we make an approximation to describe the close to horizon metric, that is the near horizon metric. And there are several works that do this, and one of them is this Shankar Narayan et al. 2005, where kappa here is the surface gravity of the black hole, and gamma is just the same invariant distance that we had discussed before. So, so the first step, as I said, is we model our horizon, we approximate our metric to the near horizon metric. The second step is to compute the effect of this massless particle in our picture. So this massless particle, as we say, we have this massless particle coming in. So what it is known in literature, or what say Tooft and Dre showed in 1985, is that a massless point-like particle in Minkowski space, the effect it has on the space-time is that it produces. But here on this slide itself, what I want to point out is that their result is valid in Minkowski space, whereas our scenario is a black hole space-time. So why is this analysis in Minkowski space important? And that is where this step 3 comes in. And what step 3 tells us, that in literature, it has been shown that a Minkowski metric can mimic the metric of a spherically symmetric black hole near the horizon. The near horizon metric, which I showed here, is mimicked by a Minkowski spacetime using certain change of coordinates. So therefore, if we have a behavior of shock wave, or the behavior of this massless particle in Minkowski space, we can extend it to the near horizon behavior using some coordinate transformation. And because this is we know the behavior in a Minkowski space, we can do QFT calculations without any problems. So to describe what this shock wave is okay, again, this Tooft and Dre 1985 paper, what they showed is that there is something called a shock wave, which is produced when there is a massless particle moving in Minkowski space. And to describe what the shock wave is if you have equation 14 is the Minkowski space-time, you make certain coordinate transformations in u and v, and equivalently, the Minkowski space can be expressed as equation 16. And what Dre and Tooft showed is that if there is a massless point-like particle moving along the v direction, that is along u is equal to constant, with some momentum p, so what effect it has on the background space-time is, or it changes the background. And if you look closely at 17, it is exactly the Minkowski space-time, a Minkowski metric, except for this term, which is in principle just a shift in v direction, v going to v plus c times theta u minus u naught, where c is related to the momentum of the massless particle. But what I want to highlight here is that if you see everywhere else except for u is equal to u naught, this is just a Minkowski space-time. Only at u is equal to u naught, there is a very large contribution due to this delta function. And this large contribution at u is equal to u naught hyperplane is what we call the shock wave. So everywhere else in the space-time, it is just Minkowski. Only at u is equal to u naught hypersurface, there is a very strong contribution, and that contribution travels as we change u, and that is what we call the shock wave. So this next slide is just I just wanted to give the coordinate transformations in which this Minkowski metric mimics our near horizon metric. And so I'll move on to the next step now. So we have a shock. What we know, the effect of massless particle is a shock wave, and we want to compute in this. We want to study the interactions between this shock wave due to this massless particle with this Hawking quanta. So in step 4, to study that interaction, what we do is we compute the width of the wave packet of the Hawking particle. And this step 4, the details I'll skip because it is not relevant for the flow of this presentation. But what I want to show is this in step 5 and 6. What we do is, how do we calculate this interaction, whether it is strong or not? We can compute the probability of the black hole's thermal atmosphere to remain in the same state after interaction. What I mean by that is that before interaction with the shock wave, we have certain width function here, which we approximate using a Gaussian, but the wave packet can be described as in equation 23. And after crossing the shock wave I said the effect of the shock wave is just a shift in the v coordinate by this quantity, and we approximate that as p. And under this approximation, the change in the wave packet will be just addition of this p, extra p in this exponential. So what we do next is we compute the probability of the particle, of the Hawking particle, to remain in the same state, which is given by equation 27. These are just some details we can skip over. But so here phi was the wave packet or wave function before interaction with the shock wave. Phi bar is after interaction with the shock wave. So the probability of having of remaining in the same state is given by the following equation. And so this is for one particle. Now, if we want the whole thermal atmosphere to be in the same state, what we do is we multiply the probabilities of each of the relevant modes. And each of the relevant modes brings in this extra n of gamma factor. N of gamma is the number of relevant modes. So what we do is, in this slide, I have just highlighted some differences from Cashier's analysis. But what I want to highlight is that when this P total is very large, means it is close to 1, it means there is a large probability of the state to remain, of the system to remain in the same state. It means the shock wave didn't have any effective interaction. So in the region where this probability is large, it is the weak interaction region. And for this probability to be, say, close to 1, we want this quantity to be very small, in the argument to be very small. And therefore, this argument to be very small is the region which brings, which is the weak interaction region. If the probability to remain in the same state is large, it means there is no effective interaction. But if this term becomes, instead of being much less than 1, it becomes similar to or of order 1, then we'll say that this interaction, what it will do is this, it will decrease this probability. That is, the probability to remain in the same state decreases. It means there is a larger probability for the state to change, and that implies a stronger interaction with the shock wave. So this condition, equation 30, will give us the strong interaction regime. And here lambda is actually related to the momentum of the incoming particle, and to fix this, of the massless particle. And to fix this momentum, we use a very heuristic argument where the de Broglie wavelength of the massless particle should be less than the black hole radius. Otherwise, just normal wave mechanics, we can say that the interaction, if the de Broglie wavelength is much larger than the black hole radius, then there may not be even any effective interaction. So the final result that I want to highlight, what we get for the width, is equation 34, which is 2h cross RH to the power 1/3. Now, h cross is actually, in this geometrized units, is related to length L Planck square, that is the Planck length square. So we do get a Planck length suppression, but we see that the gamma critical is also dependent on the size of the black hole. Now, this is a general result for any spherically symmetric black hole. And for the specific case of SADS, we have the following expression where chi is just RH by L. And what I'll do is I'll just display the results for the SADS case of the two approaches. From one approach, as I discussed in detail, the QFT approach gives us a chi power 1/3. Whereas the statistical mechanics approach, which I had not shown the result earlier, but the actual result is the second part of equation 9. So what we found is that for a usual short-side black hole, not the anti-de Sitter or de Sitter case, for the usual short-side black hole, both these approaches actually predict the same thing. And that was also found by this Casher et al. In 1997, that both these approaches are equivalent for a usual short-side black hole. But these two approaches for, like, say, SADS case, they turn out to be equivalent only in the small black hole region. So that was the main result of our paper. And so some conclusions are that a scalar field on the black hole horizon smears it. There is a smearing of horizon. The assumption of a free field propagating on a classical background is not always true. And then we computed the length scale at which the back reaction of the field becomes strong in two ways. One was a statistical mechanics approach and one was a quantum field theoretic approach. And the two results match with each other for the usual short-side black hole, but they match for the SADS and SDS cases only for small black hole cases where RH by L is much less than. Okay, that's it from my end. Thank you.
Thank you very much, Manuel. So if there are any questions, we have very short time for one question. Please raise your hand. No questions at all. Everything was very clear, Manu. Very good. Congratulations. Thanks a lot.
Thank you so much.
Okay, great. So we go on to the next speaker, which is Samved Kolekar. And Samved is going to talk about rental trajectories and rental horizons in the Schwarzschild space-time. So I am glad you managed to access the session. We all are having a lot of problems. Very good. Welcome.
Yeah. So thanks, Hernando, and thanks for the new passcode. I hope you are able to hear me clearly.
Yeah.
Yeah, okay. So let me share my presentation.
Very good.
Okay. So let me begin with my talk. So I'm going to talk about Rindler trajectories and Rindler horizons. So this would be in the background of the Schwarzschild space-time. So we are already familiar with what are Rindler trajectories and Rindler horizons in the flat space-time. So I'm going to tell you what happens when you have a black hole in the background. What happens to those trajectories? And I'm going to define them as I go along. So this is the basic outline of my talk. So I'm going to tell you first the motivation, why I wanted to look at the so-called Rindler trajectories and horizons in the Schwarzschild space-time. And then I'll give a particular definition of how do we basically define what are Rindler trajectories in a curved space. So I'll tell you that these will be basically linearly, uniformly accelerated trajectories. So we are all familiar with the definition of uniformly accelerated, but in the curved space-time, I'll tell you that we'll need something more. Okay. Then after telling you what the solutions are, I'll tell you some nice features of these Rindler trajectories in the black hole space-time. So there are these interesting bounds on the acceleration, magnitude of the acceleration. And I'll end my talk by talking about the structure of the corresponding Rindler horizons. So there is already the black hole event horizon, but because now you have these additional Rindler trajectories, there are, in addition to the black hole event horizon, there are also these Rindler horizons. So I'll talk about these, and my talk is based on these two papers, which I have basically displayed over here. Okay, so let me begin with the motivation. Yeah, so it has to do with this particular result. So we know that there is this analogy between the Hawking radiation from black holes and the Unruh effect in flat space-time. So the usual Unruh effect, which we are familiar with, is the following: that you have a inertial observer who sees vacuum, and then you have another observer who is uniformly accelerating. And the uniformly accelerating observer basically sees a thermal radiation with a temperature proportional to the magnitude of its own acceleration, provided he is moving in the inertial guy's vacuum. The question that we asked is, okay, in the works which I have displayed at the bottom of the slide, what happens if you start with a thermal density matrix to begin with? Okay, so the thermal density matrix is with respect to the Minkowski vacuum state. Okay, so instead of the Minkowski vacuum state, you are starting with a thermal density matrix, and it is defined in terms of some temperature parameter, let's say T prime. And then you have this accelerating observer whose acceleration is A. So I can define this another parameter T using this particular relation. And this accelerated observer is now moving in this background thermal bar T prime. Then what does he see? So then you can do the usual computation, QFT computation. You can compute the reduced density matrix. And what happens is the reduced density matrix is basically symmetric in terms of these two parameters, the T prime, the thermal bath which you started with, and the let me call this acceleration temperature. Okay, so it basically tells you that just looking at the reduced density matrix, there is no way to distinguish whether one is accelerating with acceleration equal to that acceleration temperature T through a bath of T prime, or the other way around. So you could have started with the thermal bath at this particular temperature T, and you could have accelerated with an acceleration related to T prime. So there is perfect symmetry. So this is because of the reduced density matrix. So the claim here was there is a kind of a indistinguishability between the thermal and quantum fluctuations. The thermal fluctuations due to the thermal bath you started with, and the quantum fluctuations because we know the vacuum state fluctuations, they appear to be thermal. So there is a indistinguishability between over here. Now we have this interesting result. Now one could ask what could happen in the case of the Schwarzschild spacetime. So in the Schwarzschild spacetime, we do have the Hawking radiation. And this Hawking radiation is, let's say, measured by these stationary observers. So these are the R equal to constant usual stationary observer. So if they have a thermometer and if you have the Hartle locking state, let's say, then we know that they are going to detect this thermal radiation. But over here, the uniformly accelerated observers, the acceleration is ultimately also related to the scale in the problem, which is just the mass. So the Hawking temperature is related to the mass of the black hole, and then the acceleration over here is also related to the same mass. So the question is, are there other uniformly accelerated trajectories or Rindler trajectories in the background of the short shell spacetime, so that you could have another parameter to play with? One parameter would be the mass of the black hole, okay, which gives you the usual Hawking temperature. And then if you have additional Rindler trajectories in this background, you have that additional acceleration parameter which you can play with. So that would be corresponding to the picture that I'm talking about, that you would have Rindler trajectories in the black hole spacetime. So there is another motivation. This has to do with the gravitational memory effect for uniformly accelerated worldlets. So when one studies basically how to implant the super translational hair on a Schwarzschild horizon, one uses this particular construction which was given by Hawking et al. And they studied basically BMS type shock waves which basically fall into the horizon. So once this shock waves basically fall into the horizon, it affects the observers which are outside. So if you have inertial observers, you get the usual familiar gravitational memory effect. But the interesting observers in this particular case, if you want to talk about Hawking radiation, would be the uniformly accelerated observer, which I just argued, which see basically Hawking radiation. So to understand what happens when you have this BMS type shock wave which falls in, how does it affect those observers? You need to first understand how to talk about Rindler trajectories in the curved spacetime. So then if you could basically work out what happens to those congruence of trajectories when the shock wave basically passes, you would be talking about a corresponding memory effect for uniformly accelerated observers. So this is basically described in the works which I have shown below. Okay. So now let me go to the main question. So how do we basically define the Rindler trajectories in curved spacetime? So in flat spacetime, we know they are basically the orbits of the boost killing vector, and they are essentially planar. So they lie in one plane. They have uniform acceleration. But the concept of planar is not properly defined in a curved spacetime. So we should have a covariant definition of what do we mean by planar trajectories. Okay. So if you just impose the condition that you need uniform acceleration, you would just fix the magnitude of the acceleration vector, but it would be still free to move on this S2, which is orthogonal to basically the direction of the uniform force velocity. So that doesn't fix. So you need to basically support some additional condition. And that is what we need, the covariant definition. So here is where this construction comes about. So this is the Letov-Frenet equations. So this is the generalizations of the usual Frenet-Serret equations which you have learned in differential geometry. So you have the curvature scalar and the torsion scalar to describe a curve which moves freely in the background three-dimensional Euclidean geometry. But now since we want to talk about the four-dimensional space-time, we basically generalize it to what is known as the Letov-Frenet equations. So they are again in terms of the usual four tetrad vectors. So in the three Euclidean geometry, you had three basis vectors. Here you would have four. And then you basically describe how the four tetrad vectors, they basically move around as you go along the trajectory. And then by imposing this Letov-Frenet equations, which is the generalization of the Frenet-Serret equations, you come about to three scalar parameters. So one is the curvature, the other is the torsion, and here you have the additional third parameter, which is the hypertorsion. And here, if you want to define what is a planar trajectory, you basically impose that your torsion and hypertorsion is zero. So that guarantees that you basically start from a given plane formed by two basis vectors out of this tetrad, and you continue to lie in the plane formed by the same two basis vectors. So the whole trajectory just is dragged along in the same planar fashion. So that is one particular definition. And it leads us to one particular constraint, which I have highlighted here in red. Okay. So it basically tells you that if you construct this change in the acceleration vector as you move along that particular trajectory, let's call that vector W. So then W should be basically proportional to your proper velocity vector, for velocity vector. And the proportionality factor is basically your mod A square. So if you impose this particular condition, you would basically satisfy the constraint that your torsion and hypertorsion becomes zero, and your curvature scalar, it becomes a constant, and that constant is related to the magnitude of your acceleration. So what does these technicalities basically tell you? That if you just take any event on that particular trajectory and construct local inertial frames over there, in that local inertial frame, your trajectory would look exactly locally hyperbolic. So the exact same way that you would view the Rindler trajectories in flat space time. So that is what this construction guarantees. So it basically guarantees local hyperbolicity all the way along the trajectory. So that basically guarantees the planar condition that we were after. So now if you use these covariant conditions, you can now try to solve what happens when you have the background Schwarzschild geometry. So we would be trying to solve this. Now one note that the usual R equal to constant trajectories, the stationary observers which we are familiar with, they obviously satisfy this constraint. So they are already the Rindler trajectories which we know, but we want new trajectories in which we also have the free acceleration parameter, which I described before. Okay. So the picture is the following, what we want to try to understand. So the red curves, this red dotted curve over here is the usual Rindler horizon in flat space. Okay. But now let's say you introduce a black hole over here. So in this picture, so this is just a schematic picture. It's not the exact solution. If you just introduce a black hole, let's say far from this particular observer, then you would expect the picture to distort. So the horizons would be distorted because now it would be following the geodesic motions in the Schwarzschild background solution. And obviously this red dashed curve which I have shown over here, this is some sort of the distortion of the Rindler trajectory. So we would try to understand what happens to this Rindler picture in the background of the Schwarzschild geometry. And the way we construct is by using this particular constraints which I described above. Now, one can find the solution exactly by solving these particular equations, and one arrives at some sort of incomplete elliptic functions. Okay, so I have shown you the trajectory over here. So this is basically the exact solution. And just looking at the expression, it doesn't look very inspiring or interesting. So I'll just highlight what are the interesting features. Okay, so to highlight the interesting features, let me first compare it with this usual diagram in the Schwarzschild, in the Rindler diagram in the flat space. So that is what this particular diagram is. So the features that we know are the following. So these are the usual hyperbolic curves. Each hyperbolic curve has different acceleration, and they have the same Rindler horizon. So this is the future Rindler horizon. This is the past Rindler horizon. This is the bifurcation point. The higher the acceleration, the closer you move to the left, that is closer to basically these horizons. That is what the feature is. So there are two parameters. One parameter is basically the magnitude of acceleration, which basically selects one of these hyperbolas over here. And the other parameter is basically the shift parameter, which basically shifts this particular origin. Okay, so that basically displaces this whole wedge either so to the left or right. So either you can take it to the negative side of this x-axis or the positive side of the x-axis. Okay, so we have two parameters. So let's call the shift parameter to be the parameter h, which basically determines our asymptotic data. So because that is where what determines the asymptotes of these Rindler horizons in the flat space. Now, we would like to understand what happens if you have the Schwarzschild background. Now, interesting things happen. So the one thing which happens immediately is if you now have the Schwarzschild background, if you try to find these Rindler trajectories, okay, the solutions are the following. So you are again looking at something which comes from infinity. So it comes from r equal to infinity. So that would be something over here. It comes around, it has a r minimum, it has a minimum turning point, and then it goes back to infinity. So it's basically, we are looking at purely radial motion. Okay, so these trajectories, they come in from infinity, they have a turning point, they have a minimum r radius, and then they turn back and go back to infinity. So the acceleration is basically pointing outward. Okay, now in Schwarzschild, if you try to increase the acceleration for such trajectories, okay, you don't go closer and closer, let's say, to the event horizon. What happens is after some point, the trajectory automatically goes into the horizon. Okay, and there is a minimum radius, and that minimum turning point is always greater than the event horizon. So for all finite choices of this asymptotic initial data h, which is analog to that shift parameter which I described. So you choose any one particular shift parameter, and then you try to vary the acceleration. What would happen is, sorry, yeah. So if you try to increase that acceleration parameter, okay, you don't go closer and closer all the way up to the horizon. There is a minimum radius which is greater than the event horizon, and that describes the turning point. So if you try to increase the acceleration beyond that, you basically are forced to fall into the horizon. So these are the bounds of acceleration that we found. So one particular bound is interesting. So in this case, if you choose h equal to 0, your minimum radius is 3m. So this is the usual photon sphere that we are familiar with. And corresponding to this r minimum, the acceleration bound turns out to be this particular value, and you can check that this value is inverse of the shadow radius. So the shadow radius for the Schwarzschild black hole is exactly inverse of this particular parameter. And the minimum radius up to which that trajectory can go is basically the photon sphere. So you get interesting physics just by studying these trajectories too. So this was about the bound. Yeah, so these are the pictures for the Rindler trajectories. Yeah, so I hope you can see the picture over here. The other interesting point is, for a given particular h, if you try to vary the acceleration, you can immediately see from these pictures that the Rindler horizons and the Rindler horizons are not going to be the same. So in the flat picture, just fixing a particular h, okay, for different accelerations, all the congruence of hyperbolas or the congruence of Rindler trajectories, they had the same Rindler wedge. They had the same Rindler horizons. But now, just fixing the h is not sufficient, because if you try to vary the a, along with the acceleration bound that we have, you also see that the trajectories also have a shift. So they no longer have the same Rindler horizon. So right now, these are only the pictures of the Rindler trajectories. So this is essentially time plotted on the y-axis and radius plotted on the x-axis. And the faint gray line which you see over here, this is basically the event horizon. Okay, so that is basically the picture. Now, given when we have found this Rindler trajectories, one can also try to find out what are the intercepts, asymptotic intercepts C, which is basically the intercepts of this Rindler trajectories with the future null infinities. So you can even have an analytic expression for these asymptotes. Okay, and because of the time symmetry of the problem, okay, whatever intercept you find for the future null infinity, the same intercept would be true upon doing that inverse operation in time for the past null infinity. So you can find those in terms of the two parameters, which is in terms of the h and a. And over here also you can see that the intercept basically is a function of both. Okay, in the earlier case, in the flat spacetime case, it was actually ideally a function of only the h. But here you can see that now it also depends on the e. So that again strengthens our picture that the horizons are different for different curves with different acceleration, but with the same h. Okay, and these are the plots for the intercepts. So you can see that they are actually not all the way linearly related to h. So there are these linearly and monotonically not related to h. They are basically these kind of functions, these kind of different functions and graphs which you get in the relation between the intercepts and the h and e. Okay. So I have drawn here the Rindler trajectories, which are given here in blue in the upper two diagrams. And the red curves are essentially the Rindler horizons. So this is basically the future Rindler horizon, and this is the past Rindler horizon. So I have drawn these two particular pictures. Now, if we try to understand why these bounds are there in terms of this particular pictures, we have an interesting point. So let's say you fix a particular h in this particular diagram, and then you try to increase the acceleration. So if you try to increase the acceleration, the blue curve should basically shift to the left and left. So that also drags this particular bifurcation point to the left, because I said that the horizons are now different for different trajectories. So if you try to increase the acceleration and move the r minimum to the left, the r null, which is the bifurcation point, it also moves to the left. And the gray line which you see over here, this is the Schwarzschild event horizon. So there comes a particular point beyond which, if you try to increase the acceleration, what happens is this bifurcation point, it goes and hits the event horizon first. But the r minimum, it has not reached all the way to the bifurcation. Okay, so that the flat spacetime case and the Schwarzschild geometry. So and hence you can think that the bounds exist, because the bifurcation point, it hits the event horizon first. So here I have shown it here for two different h. Now, based on this construction, one could ask what is the co-moving coordinates, or can one write down the metric in the co-moving coordinates of these new Rindler observers. So I have shown here the one particular form. So this is in terms of the conformal form in terms of the T and R. Okay, so I have written here the metric in terms of the null co-moving coordinates, and in the conformal form only in the TR plane. The angular plane, the angular part of the metric just hands around additionally. So now you can see that you have this time dependence also. That is true because we only know one time like killing vector in the background Schwarzschild geometry, which is associated with the usual the time coordinate of the Schwarzschild metric. And if you try to adopt the co-moving coordinates of this Rindler observers, then the proper time of these Rindler observers, they need not coincide with the orbits of another time like killing vector. So you would expect the metric to be a function of the time coordinates as well, the proper time coordinates as well. So, and that is what you see from this particular structure. Okay, so that was the part that we have completed. The next part that we wanted to basically ask was, now we have a metric with basically two parameters in the problem, the acceleration parameter and the mass parameter. So it would be interesting to basically set up the QFT in this particular background and then ask what happens to the different states. So suppose we know that the Hartle-Hawking states looks like the thermal bath to the usual stationary observer, but now you have a different wedge inside the usual Schwarzschild wedge. So the usual Schwarzschild vacuum should look different to this particular Rindler wedge that we have constructed. So what is the interplay between the two vacuum states? So that would answer basically what is the reduced density matrix and whether it has a symmetric structure again in terms of these two parameters A and M. So that is the part that we would be aiming next. And another questions one could ask is, given our construction of the Rindler trajectories, what happens in the case of rotating black holes? So rotating black holes introduce some additional effects in that because of the inertial dragging of frames, satisfying the local hyperbolicity condition is non-trivial. So figuring out the solutions of Rindler trajectories in the Kerr geometry is non-trivial, and that is another things that we are currently looking at. So I'll stop here and thank you for your time.
Okay, thank you very much, Sandet. So we have time probably. Well, I don't know if Dmitry Galtsov is there. I have no news from him, from the email. I don't know if he is also having problems to get access to our session. So I don't see. Okay, let's. Okay, if somebody has any question to Sandet. No question, Sandet. A very conceptual question regarding what you mentioned at the very beginning. We don't see any differences between quantum fluctuations and thermal fluctuations.
Yes.
Well, would you say that this is because the way we describe fluctuations, I mean, from the mathematical point of view, because we take a field, we just make a perturbation according to very specific rules. And so from the mathematical point of view, it's exactly the same. But physically, thermal fluctuations are expected to be completely different from quantum fluctuations. So can you tell something about that?
Yeah, so I agree with you. So the two descriptions are essentially different. And that is what the surprising thing we found in this particular computation. So the Unruh effect basically tells us that the vacuum fluctuations, they appear to be completely thermal. So if you look at the reduced density matrix, and in this particular case, if we start with actual pure thermal fluctuations by starting with this particular thermal bath with temperature T prime, then you have basically two effects. So you do have uh, 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 the thermal density matrix, which is a thermal bath, which is defined on top of the Minkowski vacuum state. And then you ask what happens to the accelerated observer. So these two effects are going to be combined because of the difference between the two vacuum states with respect to the inertial guy and the accelerated guy. There we have the non-equivalency of the, let's say, how the fluctuations appear to both the observers. And then in addition, you have this thermal bath fluctuations. So both of them, let's say, they mix in such a way. And this was surprising that the final result is essentially symmetric. So it was basis on that fact that we basically claim that there is this indistinguishability between the thermal and quantum fluctuations. So as far as I know, it only works for this particular case that we have studied over here. The other cases are which basically these are studied in the de-Sitter case, where he considered the de-Sitter geometry which is embedded in a higher flat geometry. And then again, if you have those uniformly accelerated trajectories in the embedding space-time, and then if you look at those trajectories as a projection on the de-Sitter space-time, then you again have such a nice feature that the temperatures are basically the sum of the two temperatures. So these are the only two places where, I mean, the connection between the quantum fluctuations and the thermal fluctuations, they become evident. So
Okay, thank you.
yeah.
Thank you very much.
Yeah.
Very good answer. Thank you.
Thanks, Anand.
Okay, let's go to the next speaker. Thank you, Sandeep, again. The next speaker is Sumanta Chakrabarti. Samantha, you were also having problems with the connection with the
Yes.
passcode. Yeah, okay. So go ahead, Samantha.
Yeah. Can you see the screen?
Yes, we can see it. Eddington gravity with matter. Very good.
Yes. Yes.
So welcome. Thank you.
Okay. Yeah. Thanks. Thanks, Hernando, and for chairing this session, and thanks to the organizers for giving me this opportunity. And good morning, good afternoon, and good evening to all of you, depending on which place of the world you are in. So this is, I will talk about a different gravity model known as the Eddington gravity, and in particular how we can include matter into this paradigm. And as it will turn out, we can have a very interesting thermodynamic perspective into this particular problem. And this is something that we'll discuss in this talk. So this work and a few others have been done in collaboration with T. Padmanabhan in Ayuka, India. And in particular, I am from Kolkata in India, from Indian Association for the Cultivation of Science. Let us start with a brief outline of my talk. I guess there is some background
Go ahead. Go
noise.
ahead. I will mute everyone right now. Go ahead.
Yeah. So this is a brief outline of my talk. So I have tried to propose an alternative action in the spirit of Eddington gravity, and from which Einstein's equation with matter can be derived, which I will elaborate upon. And then I will show that this action can have a path integral description. And this path integral description is what follows from the thermodynamic nature of gravity. And I have also listed the references on which this talk would be based on. The most recent one in 2021, that is the main reference. The other two are to support some of the cases considered here. So let us start with the Eddington gravity proposal. So the normal Einstein-Hilbert action is taken to be an integral d4x and the Ricci scalar. But Eddington, in his famous book on mathematical theory of relativity, actually suggested a different action to start with, which is d4x square root of the determinant of the Ricci tensor itself. So intriguingly, this is a generally covariant object because determinant and d4x, they sort of conspire themselves, making the combination a scalar quantity. But unlike the general relativity or Einstein-Hilbert action, this action is a function of g, of course, but only through gammas. So therefore, what Eddington did, or Eddington gravity proposal effectively is to consider this Ricci tensor as a function of gamma alone, with absolutely no reference to the metric whatsoever. Then one varies this action, and it turns out that the field equation arising out of the variation is, which I will discuss in more detail as I go forward, is effectively RAB plus lambda GAB equal to 0, which is the Einstein's equation with a cosmological constant. Now, the inclusion of matter in this paradigm is a bit of a, oh, I'm sorry, did I do something wrong? Okay. Is a bit of a problematic because the matter Lagrangians in general doesn't depend on the Christoffel connection gamma. And therefore, we cannot include it because suppose I add to the action a matter Lagrangian L matter,
which depends only on metric and some matter degrees of freedom, then variation with respect to gamma would again land up to the same equation, which is RAB plus lambda GAB equal to 0, while variation with respect to the metric will effectively tell us that TAB is 0, and we would be back to the square ones. So therefore, addition of matter seems a bit of a challenge, and this was achieved much later in 2010 effectively by this paper by Bernados and Ferriere. And of course, earlier there were other attempts to do it, particularly by Vollich. And later on, there are some other applications which was worked out by Delsate and Steinhoff. And there are a few more references which can be found from there. So effectively, the proposal is to modify the action and think of it as a function of gamma, the metric G, and the matter degrees of freedom psi. So what one does, one first varies the action with respect to the metric, that is delta A upon delta G, and then one sets it to 0, which yields the equation of G as a function of gamma and psi. In principle, this can be solved to give this. Then one substitute this back into the action, and now the action becomes a function of gamma and psi, two variables. So variation with respect to gamma yields the field equations for gravity, while variation with respect to psi yields the corresponding matter field equations. And they both differ. I mean, the gravitational field equation, of course, differs from the Einstein's equation. In a few cases, the matter field equation also differs from the reasonable one. And therefore, there are strong constraints on both of these departures from both Einstein gravity as well as in the matter sector. So none of the approaches that, as far as I know, in this direction provides Einstein's equation in any form. So due to that reason, we proposed a new action for Eddington gravity, which is effectively the same action as Eddington proposed, with RAB replaced by RAB minus kappa. Kappa is 8 pi g, the gravitational constant, times T bar AB. And the T bar AB is nothing but the trace reversed energy momentum tensor, which is TAB minus 1 by D minus 2 TGAB. So I have used a generic dimension D here, but all the calculation goes through for any D greater than 2, and therefore it holds in 4 dimension as well. So here the Ricci tensor depends on the connection alone, while the T bar AB part depends on the metric and the matter degrees of freedom. So the job is now we will vary this action with respect to the connection gamma and see what comes out of it. What equation do we get, and how do we get the matter equations in particular? Should we vary the matter degrees of freedom, or can we use some other trick to get the matter equation of motion? So first of all, to proceed in that direction, to vary the action itself, we first map the components of the RAB minus kappa T bar AB to a matrix curly MAB. I would like to emphasize one point over here, that normally we take the Ricci tensor RAB to be symmetric in its indices, but that is not the case over here. We have to take the symmetric part of the Ricci tensor, because there is a part of the Ricci tensor which is del B of gamma CAC. Now that part, if gamma can be written in terms of the metric, is effectively del A del B of log root minus G. But in this derivation, we are not assuming any connection between gamma and G to start with, and therefore that particular statement that gamma is derivative of log root minus G doesn't hold true, and therefore R is not necessarily symmetric in its indices. So that's why we will always keep RAB as the symmetric combination whenever the action is concerned. Now, having obtained this matrix curly MAB, we define an inverse matrix, which is of course straightforward, because the determinant of MAB has to be non-zero. Otherwise, the action itself would be ill-defined. Now, having obtained the inverse matrix, we also assume that it is both the left inverse as well as the right inverse. This inverse matrix is also mapped to another tensor, capital NAB. Now, the variation of the action involves variation of the determinant, and we know variation of the determinant of a matrix involves the inverse matrix and variation of the matrix itself. So this is what the first line over here depicts. The variation has a determinant part. It has the inverse part, which is this tensor NBA, and then it has variation of MAB, which is defined over here. Now, variation of MAB, that there is no contribution from T bar AB, because for most of the normal matter fields, it is independent of the connection. So we just have variation of RAB due to the variation of the connection, and that can be expressed as covariant derivative acting on variation of delta gamma. Now, this can be properly modeled in the sense that it can be converted using this alternating tensor delta, which I have just defined here, times n and covariant derivative of delta gamma. Rest of it is very simple, just like any action, we convert it into a boundary term and an equation of motion or the field equation type term. However, for Einstein-Hilbert action, there are unpleasant surprises. In particular, it is well known that the Einstein-Hilbert action actually leads to an ill-posed boundary value problem. What I meant is the following. If you vary the Einstein-Hilbert action, then you have two terms again. The Einstein's equations are of course there, which is a second order equation in the metric. But what you fix on the boundary are metric, its tangential derivative, and its normal derivative all together, which of course is not consistent with a second order field equation like Einstein's equation. And therefore, one has to add the additional terms like 2k root h, which is the Gibbons-Hawking York boundary term for space-like or time-like surfaces, and 2 into theta plus kappa into root q for null surfaces. And these two references discusses various aspects of this boundary term, in particular connection with null surfaces. However, in our case, that is for the case of Eddington gravity, I have expressed the variation over here. So as you can see that the first term is a total derivative, and it only depends on delta gamma at the boundaries. The second term, which is presumably the equation of motion term, depends on derivative of this object n and derivative of capital N. Now n and m, they both depends on gamma as a first derivative, because m is effectively RAB, and RAB depends on the first derivative of the connection. Therefore, this is a second order differential equation for the connection. So we need to fix gamma on the boundary, and that is exactly what this boundary term does. Thus, unlike the Einstein-Hilbert action, the boundary value problem associated with this modified Eddington action is well posed. Very good. Then we go ahead and talk about the field equations. So if we set the variation of the action to be 0, then we obtain the field equation after certain manipulations, like taking the trace and then subtracting it out and so on and so forth. We obtain that covariant derivative of square root determinant of that tensor MAB with its inverse to be equal to 0. And it turns out that the solution of this differential equation using the equivalence principle takes exactly the form of Einstein's equation with a cosmological constant. Now, normally, one should go ahead and vary the action with respect to the matter degrees of freedom as well in order to obtain the matter equations. But we notice that we do not have to call them dynamical, in the sense that if we just use the Bianchi identity, that eventually guarantees that covariant derivative of TAB should be 0. And we know that the conservation of TAB is equivalent to having the field equations for the corresponding matter field. So we also have obtained the matter field equations at a single go. So we not only have the Einstein's equations only, we have no modifications whatsoever. And additionally, we also have derived the matter field equations without any further hassle. There are some comments that I would like to make on this result. So first of all, unlike the Einstein-Hilbert action, where the cosmological constant have to be added by hand to the action, here the cosmological constant appears naturally. Actually, the validity of this action principle requires a non-zero cosmological constant, since determinant of RAB minus kappa T bar AB is effectively proportional to the cosmological constant itself. So the inverse metric would not be defined if the cosmological constant is 0, and the approach will fail. So it requires existence of a non-zero cosmological constant. Second, we varied only the connection, nothing more, in order to get the field equations for gravity, and the matter equations follow from the Bianchi identity itself. Thirdly, finally, we have the metric as dynamical variable, in the sense that in this Einstein's equation, we can identify the metric and the fact that it depends on double derivatives of the metric and so on and so forth. However, it is really not dynamical because in the action, we have not varied the metric in any way. So it's like a dynamical variable, which is not dynamical. And this is something which is very keen to the thermodynamic aspects of gravity, where metric has a thermodynamic meaning, and therefore it should come from some more fundamental degrees of freedom, and it should not be considered as dynamical in a true sense. Secondly, the similar action which we have written for the case of Eddington type gravity, it can be constructed for other modified theories of gravity, in particular for Lovelock theories of gravity as well. And as we have shown that all of that is possible, and you get exactly the field equations for Lovelock gravity arising out of this. Now let us talk about another alternative action, which is again purely motivated by the action which Eddington wrote down. So here, instead of taking determinant of RAB minus kappa T bar AB, we considered it to be log determinant of descent. And then determinant of G has been added just to make it covariant. So here also connection is the dynamical variable. And if you follow the same path where you vary the action with respect to gamma, and then you set the boundary term to 0, and then you get the field equation, you will see that it leads exactly to the same Einstein's equation, and the matter field equations will certainly follow from there. It turns out that this particular action principle can actually be derived from a path integral prescription. So here I provide a path integral origin of this action principle as advocated at the beginning. So what we had this tensor MAB, which is RAB minus kappa T bar AB, and we multiply it with two vector fields, VA and VB. Then we have a few degrees of freedom in our system, which includes gamma, G, psi. I mean, G and psi should not be considered as 2 degrees of freedom because we are not varying them. But VA, of course, can be thought of as a degree of freedom. And then if we want to eliminate all those vector degrees of freedom, because ultimately we do not want an action with an arbitrary vector field hanging around, then we should integrate out over all those vector fields. That is, there should be a path integral over VA. And that integral is a Gaussian integral because VA only appears twice in the exponential. It can be performed easily, and the corresponding result is log determinant with a root determinant G, log determinant of MAB. And this is the effective action, as we know. And this effective action, if you recall, is precisely what we had considered over here. So this means this type of an action, which is motivated from the Eddington's perspective, comes from an gravitational Lagrangian at a more fundamental level. And if you path integrate over all these vector fields VA, then you get back the Eddington's Lagrangian, or the modified one that I have shown. And then you vary that action and you get back your Einstein's equation. Now, where do this Lagrangian came from, which is this VA-VB multiplied Lagrangian? It turns out that this Lagrangian actually comes from the thermodynamic description of gravity. So there are effectively two terms in this Lagrangian. One is RAB VA-VB, and second term is T bar AB VA-VB. Now, how we should interpret this or both of these terms? So as the previous speaker explicitly mentioned, that for black hole horizons or for Ringler horizon, there are certain thermal characteristics that can be observed. And both of them are null surfaces. So therefore, it is important to understand what happens when this vector field VA is actually a null vector. And in particular, those are the regimes where we can expect a thermal behavior and hence a thermodynamic description of gravity. In particular, if we have a null surface with a null normal, which is denoted as LA, then the term T bar AB LALB, which is same as TAB LALB, because T bar AB is TAB minus trace of T over D minus 2 with a GAB. So GAB LALB is identically 0 because L squared is 0 anyway. I mean, it's a null vector after all. And then we have the result that T bar AB LALB is the matter heat flux entering a null surface. Similarly, RAB LALB term can also be explicitly computed, and this can be shown to be related to the change of heat content. That is, what is the change in temperature of the null surface as seen by local Ringler observers, and what is the change of the area of the null surface, which is related to the change of entropy. And therefore, this RAB LALB term can also be related to the rate of change of heat content of the null surface. Now, if we have an equilibrium situation, what should happen? These two should be equal because the total amount of heat flux coming from the matter sector should balance the total amount of rate of change of heat of the null surface or in the gravitational sector. And that is why it makes sense to talk about extremization of this combination, which is RAB minus kappa T bar AB LALB. And the extremization will denote the existence of a thermodynamic equilibrium and should be taken as an appropriate action for the path integral. So if we think of it in the following way, so originally we have some gravitational degrees of freedom, which are not metric in the sense that metric emerges from those degrees of freedom. So those degrees of freedom can be thought of as being null in nature, maybe, with LA and LB as their vector fields, as their characteristics which are being denoted by them. And then this RAB minus kappa T bar AB, LALB, that sort of gives us the equilibrium condition. And that we can take as our action. Now, this action depends on those microscopic degrees of freedom, whatever they are, through this vector field LA. And therefore, if we want a classical contribution arising out of it, we must path integrate, or we must integrate over all those vector fields. That is precisely what we have done. And that leads us to an action which is log determinant of RAB minus kappa T bar AB, which is by the Eddington's approach, which we have discussed, provides us Einstein's equations with matter and a non-zero cosmological constant. Also, for this Gaussian path integral to make sense, it turns out that the cosmological constant has to be positive. Otherwise, this determinant would have some negativity issue and convergence can be questioned. So therefore, the bottom line is we showed that there exists a Lagrangian with a thermodynamic interpretation, as various previous works have suggested, which has some extra degrees of freedom in the form of the null vector LA. If we integrate out these null degrees of freedom or these additional degrees of freedom in order to obtain an effective action, which only depends on the geometrical degrees of freedom, so to speak, then the corresponding action is equivalent to Eddington's gravity, except for some change of cosmetics from determinant to log determinant and so on and so forth. And it also solves the problem of addition of matter to Eddington gravity in the sense that TAB arises very much naturally into that framework. And what is more is that you get a positive cosmological constant out of that, which none of this were possible from the case of Einstein-Hilbert action. So I will just finish with a few conclusions from my side. As I mentioned, we have provided an alternative way of introducing matter in the Eddington gravity paradigm. We have showed that variation of the connection yields the Einstein's equation with a positive cosmological constant, or at that classical level on the cosmological constant. And imposition of Bianchi identity yields the matter field equations. Similarly, we can write down another action which is very much similar in spirit, and that can be obtained from a path integral prescription and with a more fundamental action which is RAB minus kappa T bar AB, VABB or LALB, and that is originating from the thermodynamic description of gravity. So with that, I think I have finished up my time slot. So thank you very much for your kind attention. So questions, I'll be welcome.
Thank you very much, Samantha. So we are waiting for Dmitry, who is trying to enter our session. Nothing is working for him. So let's wait a little bit
for
him.
Maybe you can suggest him to try it from the browser, because I could not do it from the app. From the browser, it worked.
Okay, I will tell him. So in the meantime, if there are any questions, please go ahead, ask the questions. I will try to contact Dmitry. No questions?
Yeah.
There are two questions, sorry. Charles?
Okay.
I have just a brief question about one of your pieces of notation. I think I missed where you defined it. In your path integral equation, what is capital L?
So capital L is sort of a length scale which we have introduced to make things dimensionless. I mean, you can think of it as Planck length if you wish. I mean, effectively, there is an overall, see, D4X has to be made dimensionless. So there is just a length scale L which is associated with that. I mean, it can be anything. I mean, it will not appear in the final effective action. I mean, in the sense there will be something inside determinant again to make it dimensionless. But when you vary it and get to the equation of motion level, this L will not contribute. So this is just like if you set, yeah, CG and H bar to 1, like in natural units, then this L would be unity. But if you want to keep track of the dimensions of your objects, there would be such a length scale L.
Okay, so would the choice affect any thermodynamic quantities?
Not really, because you see that L square is sort of multiplicative. What we need is this MAB VAVB, which I have written below as L grav. So therefore, whether L square is present or not, this term, the interpretation for this term still remains.
Okay.
So the thermodynamic aspects will be there, but you can sort of think of this L as a length scale beyond which you should not trust this theory, or maybe you should talk about scales larger than L. So that sort of an interpretation can also be given, because of course this is not the fundamental description. There has to be something more, possibly quantum gravity origin from which this should emerge. And this L may be a length scale which distinguishes these two regimes of, of gravitational interaction.
Okay, thanks.
Thank you. Other
Okay, Swastik.
Yeah. Hi, Sumanta.
Hi.
So it's a very interesting talk. I was curious about one thing. The fact that you are doing a Gaussian integration, path integral, and integrating out this vector field degrees of freedom. I mean, this
Yes.
to some extent is reminiscent of, like, if there is a gauge symmetry, you integrate out the fields. So is there a symmetry angle to this? I know that this is, of course, it has a different mathematical structure, but still I am curious if there is a gauge symmetry or some symmetry angle to this integrating out.
Yeah, there can be one. I mean, just to briefly mention that, as I mentioned, when you think of this vector field as a null vector, then what happens is that if you add, I mean, RAB to anything which is like some constant times GAB, then that vector does not contribute. So whether, which is sort of a symmetry of this gravitational theory. So whether that symmetry is what is present here, that needs to be seen, because the only catch here is that this vector field VA, when I'm integrating, I'm sort of assuming that I have gone to an Euclidean level, while the null vectors do not necessarily have a proper Euclidean continuation. So that part we have sort of bypassed by considering a limiting procedure, but whether that introduces some additional symmetry or some difficulty, that needs to be seen. Or otherwise, what one can do, one can impose that symmetry condition, effectively the null condition, by using a Lagrange multiplier. And that will also lead to a very similar set of equations, but you can think of those as arising from some symmetry, maybe. The symmetry that we are working on a null surface norm is 0, that kind of an origin.
I see. Okay, thank you.
Okay, thank you.
Okay, it seems that Mitro is still having some problems. So Subhuti, you have a question? Go ahead, please.
Yeah, please.
Subhuti, we can hear you. The microphone is off. Subhuti?
Yeah.
Hello, am I being heard?
Yeah. Now you are audible.
Yes. Why cosmological constant comes out to be only positive? Or did I get
that is because when I'm doing this particular path integral, then I should get out this determinant of MAB over here. Now, if I go back to the field equations, which is a few slides ago, when you see this RAB plus lambda GAB, so here you can show that RAB minus kappa TAB, that will appear here as minus lambda times GAB. And determinant will turn out to be positive only if the lambda is a positive quantity. However, here, if I want this path integral to make sense, then I need the determinant of this quantity to be positive. Otherwise, this is a Gaussian integral and it will not converge in other limit. So that actually tells me that the constant, which is effectively the cosmological constant, should be positive because this MAB should have a positive definite determinant. So that was the idea that we used in order to argue that it should lead to a positive cosmological constant. Just from the convergence of Gaussian.
Excuse me, isn't that a limitation in what you're presenting?
I would not say so because the 4D world, as we know, has a positive cosmological constant. So I would say it's a good thing that a positive cosmological constant comes out rather than a negative one.
No, I mean, suppose that I wanted to create a world with negative cosmological constant. Would your formalism work?
Yeah, so the point is, if you just take the this action, which is at purely classical level, then of course it will work. It does not matter whether you have positive cosmological constant or negative cosmological constant. So inclusion of matter will work irrespective of that. But if you want to have a path integral description, then of course you need a positive cosmological constant. So this part will work with a positive cosmological constant.
Thank you.
Yeah, thanks.
Charles, do you have a question?
Oh, I'm sorry, I forgot to put my hand back down.
Okay. So Dimitri is still trying to get access. He's changing his computer. Let's see if it works. So if anybody has any question to any one of the speakers of today's session, please go ahead.
So maybe I should stop sharing if.
Let me ask you a question. I'm switching between different computers. So when you propose this generalization of Eddington's theory to include an energy momentum tensor, this new energy momentum tensor you are getting there depends on the trace of that tensor. What happens, for instance, in the case of Maxwell's theory, in which the trace is equal to 0?
Yeah, but I did not include the trace, so it will, I mean, the trace is just here, so it will be TAB only, I mean, since the trace is 0.
It's not a problem at all? Because
no, it's not a problem.
This is very important for the field equation, so it doesn't matter.
Yeah, it doesn't matter. Yes,
okay.
yes.
Okay, very good.
Yeah.
So any other questions to any one of the speakers today? If no, okay, let me try to help Dmitry. In the meantime, please wait. We only have 10 minutes left. If you have any questions, please go ahead. Let me try to help Dmitry to get into our session with a different password. Okay, just a minute, please.
Okay. Oh, sorry. Sorry.
Very good, Dmitry. Finally, you did it.
I
Okay.
don't know. I entered finally this yesterday password after many attempts. Maybe they did something. Okay.
Yeah. I am sorry. We are all having problems with our passcodes for some reason. So, welcome. So go ahead, Dmitry.
Yes.
Just let's share your screen.
Yes, I am sharing.
Dmitry?
Yes, yes, just a moment.
Okay, very good.
Yes, good.
Very good, we can see it.
Okay, so this conference was celebrating the beautiful poster. We can see that celebrating mass formulas. So it is just a talk about that. And I start from a short theory. It started 50 years ago by the famous work by Christodoulou, Ruffini, Smart, Hawking, Hartley, Wittgenstein, and others. I just say a few words about Smart. Smart took the Kerr-Newman formula and differentiating this mass, he obtained this relation with something for T. He did not know about T, and he said that is horizon tension. Also referring to Wittgenstein, who just defended his thesis that time. Omega was clear and the potentials too, but the T was interpreted as horizon tension. But actually his aim of that famous paper of 74 was to establish a non-differential formula. And that non-differential formula also include this T, which was for him, it was tension. And then the big progress was made by Carter in this direction in famous lecture in the Zeus school. And he started from common definition, which is common now, definition of asymptotic masses at infinity. And this can be transformed by Gauss theorem to the surface of the horizon and the contribution of the bulk, whereas R is Ricci tensor. And if Ricci tensor is 0, so he obtained the formula which is well known. This is smart formula. In terms of already surface gravity and the area of the horizon. Now, it's already our work with Gerard, Clément. We can go further using Tomimatsu. Tomimatsu approach was to reduce these integrals, bulk integrals, if R mu are just Maxwell field, just for that case, and using Weil-Papa-Petro parameterization, of course. So there are some beautiful constellations which allows you to present the bulk contribution as a divergence of some vector, and then it is reduced to the surface integral over the horizon. The same for bulk contribution to the momentum, angular momentum. So finally, we have to add the gravitational contribution. This is just the Komar integral, which is expressed in the metric already, and for momentum too. And then the crucial point that you have to dualize the electromagnetic to three-dimensional reduction of Maxwell in Chain-Maxwell system. So Tomimatsu used the Ernst potential. It is not necessary, it is just the magnetic potential, which is produced by dualizing the AV component of the vector potential. Now, also dualization of omega rotation, which is here, to twist potential. It is something like that. In presence of Maxwell fields, there is additional term here, and this is two-dimensional notation. I here is rho and z. Then you have to calculate something, so you transform to that form using this chi, twist potential. Then you use it, it is a horizon, actually the horizon. And then Veil coordinates, the horizon is just the rod along the axis, the rod which is at rho equal to 0. So it looks like one-dimensional subspace, but it is not, because it is singularity in Veil coordinates, and the area is finite, we will see. Now, also the rotation parameter takes a constant value, which is just the inverse of angular velocity of the hole. Now, after that, we reduce the whole integral over common integral over horizon, and I just call it MH as gravitational plus field contribution. Both are there, and again using some properties of the horizon. I can simplify that. I need the details. And the constancy of the magnetic potential, electric potential in the co-rotating system. So it is known that on the horizon you have kappa, which is constant self-gravity. And also in the Einstein-Maxwell case, it is electric potential of the horizon, which is not AT, but shifted. It's in co-rotating horizon. Okay. After that, you still have to do some transformations in presenting in that form. And this differs from Tomimatsu by the last term. It is just the problem of calculations. If you do it accurately, you have this term. I don't know why Tomimatsu forgot that, I don't know. But there was a discussion in the literature that Tomimatsu was right and we are not right, but you can check. It is not, at this stage, it's not so difficult. And the same for the same manipulations for angular momentum led us to this formula, which coincides with Tomimatsu exactly. So it is only here. But the consequence of this term, which we discovered, is crucial for magnetically charged, for dions, for magnetically charged hole. It's just cancel MH, it is the mass of the hole. If it is electric mass, in smart formula, you have the charge term, phi k. But in the magnetic case, it is just tentatively magnetic, the same product, but there are no this, because it is contribution, this contribution is local and then should not be there, because the magnetic contribution is due to Misner string. We will see later. Dirac string. Okay, so after we add the same definition of electric charge and the area of the horizon in Veil coordinate is Z, so finally we obtain this formula. And this formula is valid also in presence of magnetic charges, but up to contribution of the bulk, which in that case doesn't reduce the contribution of horizon, because there is a Dirac string, and Dirac string is another object. You calculate the bulk integral using the fact that you have already two surfaces. The second will be around, there will be a cylinder around the polar axis, and you will discover that the Dirac string are really heavy. And because of that, the mass at infinity will be different. It will include this magnetic charge, but not the mass on the horizon. Okay. Now about Dirac string, there is a parameter when you introduce the vector potential, and there is a constant which you can manipulate to put the string north axis, south axis, or both. So using our formalism, you can prove that the only correct way to do is C equal to 0. But this is not so complicated. Many people also, because otherwise the formulas will be contradictory for, and they will have divergence. Okay. Finally, you add the Misner string contribution symmetric case, north and south, and both of them plus MH give you M, which is asymptotic mass. And this asymptotic mass already contains the contribution from the magnetic charge. Now we have to apply this to multiple black holes we would like, which contains also struts supporting, by double black holes, which contain struts or strings between them. Also, there can be Dirac strings and Misner strings. So all these objects can be incorporated into Rod formalism, which was developed in connection with five-dimensional solution, five-dimensional rings. It is by real Harnack. And this is also used in the technique of integrable systems, of course, in Belinsky-Zakharov way to come. So it is the same story of rods. So there it is two-dimensional, 2x2 reduction of Einstein equations, the static and axisymmetric stationary axisymmetric configurations. It is proved only in static case that each rod configuration correspond one-to-one to some solution. For stationary, it is also only believed, but it is true. So, what are rods? It is the degree of degeneracy of gram matrix GAB at rho equal to 0. This matrix, its determinant is rho, so it must be degenerate on the polar axis. And the degree of degeneracy is, one can say the following: if dimension of the kernel is more than 1, it will be strong curvature singularity. But if it is equal to 1, it will be weak singularity of the string type. So it's distributional kind of Ricci tensor. And this is just what we need. It is usually the story of struts, cosmic strings, and Misner and Dirac strings. Now, this matrix has 0 eigenvectors. These eigenvectors, so-called rod vectors, is just the part of the notion of rod structure. Each rod has his own vector. Parameters of this vector are constant on the rod, which reflects for the horizons and well-known theorems about rotation and surface gravity constancy. But now it is for the length vector at all. For instance, what is kappa? Kappa is this. Yes, kappa is a in this formalism. It is the same. Each rod vector can be continued in the vicinity as a vector of space-time. So, and the horizon and the rod itself, it is the killing horizon of that killing vector, which is generated by the same. So it's another point of view. If you have space-like rods, it is not a horizon, it is singularity, it is just the strings, Misner's, Dirac or struts. And to avoid conical singularity, or the mass will be 0, if you can identify this is another story, how whether you can exclude this, but in general case you cannot. So for the horizon, the length, the rod vector consists of kappa and omega, and the same for space-like rods. And you can introduce for a space-like rod the same, by analogy, the same quantity as you call surface gravity. I will call it space-like surface gravity. I don't about interpretations, it's more complicated, but actually, formally, it is also killing horizon, but killing horizon for that killing vector. So one killing vector well known for rotating space-time, it is, and another which is associated with space-like rods, it is that. But for instance, its norm is actually 0 because sine of theta. So finally, we calculate the contribution of Kommer. This is total Kommer masses at infinity. By Gauss theorem, we reduce to bulk and rods. Now there are many rods, including horizons, and for each rod we compute those things. So in the Einstein-Maxwell case, it is most simple, and this is given by these formulas. in presence of infinite strings, now in particular for NAT parameter, you get infinite Misner strings. You can see that there is an argument that C should be equal to 0. So again, you have to use the symmetric configuration of Misner strings too. I don't explain it. And finally, some more calculations give you the following. The mass, this is a formula which joins those definitions. And we have a rotation term, we have mass term, we have charge term, and this is should replace the area term. And it replaces it indeed, because in Weyl coordinates, if you calculate area of the horizon, it will be exactly the length of the horizon road divided by a quarter of length. And finally, you express in terms of temperature, and you will get the same as before. Now, but what about the infinite? This holds now for any this quantity which replace your horizon. This one, it holds for any road, including strings. Now, for infinity, common mass at infinity cannot be expressed now in a universal form, because we don't know which string singularities are present, and for each configuration it will be something special. But only we can write that the total mass will be equal to this contribution of rod masses for horizons if there are many black holes, and the strings, and the same form here, area of the horizon multiplied by for strings multiplied by the special surface gravity. This is example for Kernut. There are two strings, Misner strings, infinite there and there, and finite part, which is time-like vector. And these are parameters, so explicitly I have no time to explain. So finally, we can see that the total momentum will be given by the sum of contribution of whole and the two Misner strings, which are heavy and which also rotate and calculate here. And the total momentum will be AM as expected. Now we would like to generalize this to AMDA as an example of supergravity actions which have many vector fields, many scalars, but such structure which contain axion and dilaton. What is the pleasant features, and that the tensor are menu which enter through the bulk contribution to the mass. It in stationary axisymmetric case, it doesn't contain scalar fields at all. So it is only electromagnetic part multiplied by dilaton. But this multiplication by dilaton reduces to redefinition of the electric charge. So it is compensated. The only thing which is troubling now, the dualization condition is different. It contains also dual tensor and axion here. And what to be done to reduce it to the just area integrals over the horizons over over the surface of the rods, we need to exclude the bulk contribution. For the moment, it is work in progress, and for the moment, what we did is to do it excluded if A are frozen. So just I don't know, for some reason derivatives of A suppose 0. For example, for the static case, and then it works. And what I obtain is surprising. We have the same formula final. Only definition, initial definition of charge will be different. And I think that we will be able to prove it in the general case too, but calculations are somewhat complicated in that case. Now, in particular, if you exclude axion, you get dilaton, and then you can generalize it for arbitrary alpha coupling of the dilaton. Now, a few words about this interpretation of horizon as a length of rods. clearly this is reminiscent of Smart idea that it was tension due to tension. So not the surface gravity, but tension. Of course, there is a tension on the horizon. We know this from other theories, but now it is the length of the rod. And from the other hand, you know, in the Schwarzschild metric in the Wheeler presentation, its mass is just half of the rod. So you will get the same. Now, in terms of length, this formula is like that. And the question is, if it is a string, it is a Misner string, for instance, how we should interpret the Misner contribution to this contribution. This is a contribution of Misner string. Many people believe that it is also entropy. I don't know, because the entropy, it is a Killing horizon of space-like Killing vector. Inside, there is nothing. It is singularity. There is no, one can think that it is just the internal horizon of the hole, but it is not, because behind the horizon, there is also our region, but here, no. So the argument of Karlip, who was maybe the first who noticed that Misner string is the Killing horizon of d5, he considered static case. In our case, it is rotating d5. Now, the argument that you have two-dimensional, the Killing horizon, you have two-dimensional differential multiple, which requires the central charge, and this then the Cardy formula gives you the entropy. So in that sense, you can formally, but still I leave it an open question. Now, yeah, this is conclusion. So this is a common definition, sufficiently improved by Tamimatsu, and now with additional term which we found, it's allow us to, in the case of pure vector fields, to reduce the bulk contribution to the horizon, and then finally derive mass formula. It seems to be generalizable to supergravity, but it is just work in progress. I'm not. We could prove it in the static case, but it is not enough. Now, our universal mass formula may apply to any two individual rods, but for any of them, which contains also all kind of string singularities, distributional kind of matters. And now there is a discussion about entropic term of Misner string. Also, entropic may be applied in principle to cosmic string, but it is not done usually, because cosmic string it is obviously mechanical. There's just the tension which produces length term. In our treatment, Misner string and cosmic strings are absolutely the same. So there is a other argument that this length term may be more appropriate here. So thank you very much. That's all. And I apologize again for waiting.
Okay, thank you, Dmitry. I am very glad that you had finally the opportunity to give this talk. So just let me know that anytime they could switch off the connection and there is nothing I can do. We have, I would say, 1 minute, 2 minutes for questions. So if there are any questions, just raise your hand.
Okay.
Any questions? I don't see any hands. So Dmitry, let me ask you a question, a very simple question. You are using the Bekenstein-Hawking entropy formula for all these mass formulas you are deriving. How do you know that it is not necessary to apply Wald's formula, which is different in the sense that it is based on a different approach, the approach of another charge? Sometimes it happens when you add so many fields that the entropy formula changes. What happens in your case? Do you know exactly that you can use the Bekenstein-Hawking formula?
No, it is just what we would like to prove, or to see what happens for each rod, which include all horizons of black holes. You obtain not Wittgenstein, but you obtain this guy, which is the relation between the rotation, mass of this rod, electric charge, and the length of the rod. And this length term, in the case of true black hole, this length term can be shown be equal to product of the surface gravity and the area. It's just mathematically the same. But for strings for other objects, we do not have such necessity to do it, because we have to justify the entropy from physics first of all. So I would prefer to leave it as it is for Misner strings, for instance. But actually, for Misner string, you can alternatively, this is the total mass, which is contribution of holes, a contribution of strings. And here there are in particular Misner strings, but you can introduce the notion of space-like surface gravity, because the Misner string area, it has an area, finite area because of singularity. It is a finite area, and the finite quantity absolutely the same nature as surface gravity, because it is a Killing horizon over vector, but the vector outside the Killing horizon, it was space-like. Inside it doesn't exist. So the situation is different. For Hawking case, outside the Killing vector is time-like, inside is space-like, and it is now on the horizon. And in that case, you have physical reason to call this entropy mainly. In the case of entropy in quotation marks, just this term, you are not such reason. So it's our discussion. I would like to emphasize that maybe this interpretation is not motivated, is not entropy.
Okay, very good, Dmitry. So let me thank all the speakers of today's session, all the participants for their interesting questions, the speakers for their interesting talks. This was the last talk of our session on black hole thermodynamics. I thank you for the participation, and I hope to see you here in the next Marcel Grossman meeting, this parallel session. And please enjoy the rest of the conference. Thank you very much. See you.
See you, and thank you for your efforts.
You're welcome. Bye-bye. Thank you.